Okay, let's get started. Hello, everyone. Good morning, good afternoon, good evening, depending on where you are. My name is Lin Fei-Wu. I'm currently a principal scientist at JD.com, Silicon Valley Research Center. Today, I'm very delighted to welcome you all to our IJCAI tutorial, Deep Learning on Graph for Natural Language Processing. This is joint work with Dr. Yu Chen from Facebook AI, Professor Heng Ji from the UIUC and Amazon, Dr. Yunyao Li from the IBM Research, and Professor Bang Liu from the University of Montreal and Miller. So you guys want to say hi to our audience?
Hello, everyone. Welcome to the tutorial.
Okay, let's continue. Okay, so first we will, this is outline for our DLG4NLP tutorial. So in the first part, we will talk about the introduction of the DLG4NLP. Basically, in this component, we will talk about why we care about graph for NLP. And one thing I want to guys to know that the machine learning for NLPs have been already studied a very long time, and even machine learning on graph for NLPs have been intensively studied for about 2 decades. So we'll definitely talk about what's conventional machine learning technique for NLP. And then with the rising of the deep learning, so what's the modern technique, deep learning on graph for NLP? We will introduce the basic foundations of this type of the technique and to talk about some popular model like graph neuronals for the NLP task. And then we will move to our key component, the foundations of the DLG4NLP. So specifically, we'll talk about giving a text sequence. So how can we construct a graph from a sequence? Shall we use a static graph construction or shall we use a dynamic construction for the NLP task? And then once we have a graph at hand, so what kind of graph representation learning technique we should choose for different graph type? For example, it depends on graph. It's like it's a homogeneous graph or it's a multi-dimensional graph or Cosine graph. And finally, we will talk about a specific type of the model called a graph-based encoder-decoder model for NLP. Basically, this is a generalization of a successful sequence model that have been widely used in NLP domain. After that, we will talk about various applications in NLP domain. Specifically, we choose 5 different representative applications here: information instruction, machine reading comprehension, natural language generation, text clustering and matching, text mining and classification. So after that, we will talk about DLG4NLP demos, which is a demo show for our graph for NLP library, which is the first library that have been developed for make easy use of graph neurons for the various NLP tasks. And after that, we will talk about the feature duration and conclude this tutorial. Okay, let's first talk about a basic foundation for the DLG4NLP. So why we care about graph? That's essentially because the graph are generic language for describing and modeling complex system. So just I'm showing the right-hand side, right? The graph is a very simple structure. You have a bunch of the graph nodes that is represented different objects. And you have a graph edge that essentially try to describing the relationship or the similarity between 2 graph nodes. Let's give a concrete example about how we use this graph. Okay, so let's imagine this is from AI plus education domain. This is like teacher student graph. And in this graph, the node is have 2 different types, either teacher node or student node. For each of the teacher node, they also have multiple attributes associated with this graph node. For example, what kind of a class this teacher teaching, and what's the rank for this teacher, position if it's in the university, and gender information. Same thing for the students. So when we talk about the deep learning on graph today, we are essentially talking about a type of the algorithm that is taking 2 information as input. One is graph topology, typically written as adjacent matrix. Another one is assigned information associated with the graph. For example, the node attribute or edge attribute, and output will be some kind of like node classification task or link prediction task or other tasks. For example, we can predict what's the node type, teacher or student for each graph node once we're learning the representation of each graph node. Okay, so as you can see here, the graph structure data essentially it's everywhere nowadays. Okay, ranging from the social network and internet, all this stuff is naturally represented in graph. Okay, in information retrieval, like search engine or recommendation system, everyone is wrapped in a social network. And even in the financial domain, we can, today people are widely using like graph analysis for the anti-money laundering problem, where they try to modeling the transaction flow as a graph that is considered by the customer and each of the financial institutions. For the AI, today there are very hot topic called AI plus drug discovery, where people try to modeling the chemical compound as a graph and try to learning a distribution of these existing drugs, and hopefully that it can generate a new graph that represents as a new drug with a certain property. People have been also using for the program analysis, for example, to leverage the control flow graph or data flow graph. And even in the well-known computer vision domain, if we want to do the high-level reasoning, just like what is the activity inside this image, so you can easily modeling this a different high-level object as a scene graph, and then to do the visual reasoning. Of course, the graph has been widely used in NLP domain as well. So that's because that the human language is essentially a high-level symbol. Okay, so it's not a simple sequence as we see in computer or in the textbook. Okay, so there are many hidden structure information behind the simple text input. In generally speaking, we can think about as a different kind of like structure information about the sentence. It could be like it's a syntactic information, or could be semantic information. For example, we can definitely using existing past tools like a dependent part tree or constitution tree to analyze the sentence structure for the kind of text sequence. As you can see here, that they have many of the structure information behind the text sequence, and therefore that we can leverage this to augment the original text sequence to formulate a graph. And if we want to leverage the semantic information of the text sequence, we can see that we can use different other tools. For example, the AMR, the abstract meaning representation parser, to get the high-level semantic representation of the kind of text sequence. We can also use like information instruction graph to get a list of the triples that to understand what's the high-level event inside the IE graph. Even for some specific application, right? So for example, for SQL querying in the database domain. So as we know that the SQL querying is composed by the different clause, and even different clause don't really have any order information. You can easily switch them without changing any querying result. Therefore, that it's better to represent in graph format instead of use a sequence. Okay, so talk about some basic stuff about the graph for NLP. Now let's talk about some conventional machine learning technique. So people have been already used for NLP. Before that, let's talk about how we represent natural language and in general. So conventionally, people have been representing natural language at the back of the tokens, just shown in the right-hand side. So if we talk about like several sentences, welcome to attend our DLG4NLP tutorial. In this tutorial, we will present how to use the GN for NLP. You see that? So conventionally, people have been treating each of the word token as just a symbol. Okay, therefore that we can use like backward word or TF-RDF to using a sparse vector to represent either sentence or paragraph or document. And later people found that, so this is completely ignored the semantic meaning of each word token. Therefore that, within the successful technique called the word to vector technique, essentially they transform the original text token into its latent space, so that we can learning a function that to transform the original token into the latent space using a vector to represent each of the word token. And each of the vector will preserve this original semantic meaning. And this has been very, very successful starting from the 2014 and really reshaped the whole NLP community. And today, people tend to represent the natural language as a sequence of tokens, and each token is a word token represented as a dense vector, using either word vector or global vector. And even further, with today's BERT or other transformer-based technique for pre-training language model, we have been moving from using uncontinualized or context-free word vector. Today we call the word vector the context-free word representation compared to the continualized word embedding that is generated by BERT or some other pre-trained language model. But as we said before, right, you can also represent the natural language as a graph. Beyond the graph that we have been describing before, a text graph can be easily derived into a hierarchical graph. For example, a document can be decomposed as a multiple paragraph, and paragraph a multiple sentence, and sentence can be decomposed as a multiple word. Therefore, that you can easily to formulate a hierarchy of each of the elements into a graph. Okay, so here is a bunch of the conventional graph-based method for NLP. We have selected just a few of the algorithms to talk about here. So for more details, you can go to Mahase and Redep's book published in 2011 by the Cambridge Press. Okay, so we can see that. So for example, for random walk algorithm, so which is try to generate a random path to obtain a stationary distribution over all graph node. Once you learn the representation for that, you can easily to compute a semantic similarity between text, or you can also use for the lemma disambiguation task. People have been using graph clustering algorithm for text clustering as well. As long as it formulates as a graph, you can use a spectrum clustering or random walk clustering or min-cut clustering to do the task. If we try to doing some like natural language inference, like textual entailment task, you can also to try to formulate your hypothesis text and the text into two different text graphs. And then you can use in graph matching algorithm to compare similarity between two graphs, and therefore to entail is two texts related. The label propagation algorithm is trying to propagate the label from the labeled data point to the previous unlabeled data point. So in this way, you can learn representation for each of the graph node, whatever is seen node or is an unlabeled node. And therefore that you can use it for the word sense decomposition or sentiment analysis. So this is some basic introduction about what's a conventional machine learning technique. So how about with the rising the deep learning, what's a current or modern technique for the deep learning graph? We will introduce some foundation and model here. So as we all know here, before the deep learning, people have been spending a lot of time to do the feature engineering. That's because the feature engineering is the key. We all know that, so it's very important to get a feature matrix so that your learning algorithm, is really able to learn the most important information from the data. So with the rising deep learning, so we tend to using neural nets to automatically learn the feature so that we can generate a feature matrix and then send to the learning algorithm to learn the model. It's the same philosophy when we're doing the feature learning in graph. So our goal here is try to design some efficient algorithm so that we can transform the original object. For example, here is a graph node into its latent space so that we can learn this function f using a vector representation to represent each of the graph node. And therefore that, so the key here is how to get effective and impressive representation. Among the each different deep learning and graph technique, graph neural nets have been showing the great potential to tackle variance of the task. So here we are focused on the graph neural technique and talk about the foundation here. Basically, there are two different embedding we should talk about here. One is node level representation, another one is graph level representation. So in order to learn a node embedding, essentially we have to define some operation called the graph filtering operation, which the graph filtering process essentially is take a graph adjacent matrix as input and input the node embedding as input. And using different kind of a transformation, later we try to update the node embedding. And notice that so graph filtering operation don't really change any graph adjacent structure. Therefore, that if you want to learn the graph level embedding, you need to use a different operation. So depends on the type of the graph filtering operation, we can generally carry them into 4 different groups: spatial-based method, spatial-based method, attention-based method, and recurrent-based method. So Once we try to learn the graph level embedding, the new operation has been introduced called the graph pooling operation. So graph pooling operation essentially takes the input graph and the input node embedding as a two different input, and then try to generate a smaller graph with a few nodes and with new updated node embedding. Basically, we can convert them into two different groups. One is called flat graph pooling. That essentially you can use, for example, mask pooling, average pooling, or mean pooling to get a single vector that will summarize the whole graph. However, you can also use a more advanced technique. For example, hierarchical graph pooling. Essentially, they try to using a graph clustering technique to learning each of the different graph to compress the original graph into the smaller graph, and therefore that later and they can have a different layers. And finally, you can calculate all the graph level representation for the different layers of the graphs, and then to generate a final graph level representation. But in generally, in NLP domain, flat graph pooling should be enough. Okay, so now let's give you a very basic model of the graph neural, try to illustrate the basic key concept about what is the graph neural about. So the key idea here is to try to generate a node embedding based on the local neighborhood. So as shown in the left-hand graph, right? So let's say A is our target node. If we want to learn the graph representation, the representation for the graph node, essentially you try to learn the context information surrounding around the A, right? So if we only think about the first order neighborhood is the most important context information, then BCD is the most important thing that when we try to learn is the target node A. As similarly, though for B, the AC is a direct label, therefore that we can formulate a unique computational graph for each of the graph node. And then we can using a neighborhood aggregation method, try to aggregate the representation for each of the first order labels, and then try to learn a message and then propagate it to the further graph node. Note that so in the layer 0, right? So essentially we have this node attribute that is very important information regarding its original property about each of the graph node, and then we can transform the interlatent space and then do the propagation. So essentially, conceptually, the model could have actual depths, but in reality, it's not. For example, it really depends on what kind of graph neurons you are using. Typically, the number of the layers or the number of the hops is a hyperparameter you should tune. And so here is also a very important concept that currently it cannot use a very deep graph neurons because it have a strong overfitting problem. And this is one of the very active research area called deep graph neurons. Okay, so in general, so here's an overview of the graph neurons model. So first you have to define a neighborhood aggregation function so that you can aggregate each of the graph representation and to update a new representation for each of graph node. And once you have that, you can define a loss function on all the node embeddings that they already learned. And then we can train a set of the node. Typically formulated as a batch of the computational graph, and then you can generate a representation for each node. One good thing about this formulation is that so even for the node that is level C in the training phase, you can still generate a representation for each node. That's because that we are learning a graph aggregation function instead of the parameter for each graph node. Therefore, that so as long as we know the new node that connect to each of the existing graph node, we can use the aggregation function to easily generate a representation for this new node. Okay, so let's take a very simple aggregation function as an example. For example, let's choose the average function as our aggregation function. Therefore, that we try to average messaging from each neighborhood, and then later we apply a neural network to and the activation function, and then to generate a new node. So here's a very basic math behind this whole process. So basically, so here we have to average a neighborhood information as shown in the red box. So then after we average that, we call the message, okay? And then we can fuse this message information with the node embedding from the previous layer, and then to apply for a nonlinear activation function to generate a new node embedding in the current layers. Okay, so let's summarize is the key idea. Try to generate a node embedding by aggregating neighborhood information. There are two advantages. One is allow for the parameter sharing in the encoder. Another one is allowing for the inductive learning. That's why we can learn this new graph node representation, even though we didn't see that in the training set. Okay, so after introduce a very basic graph neural model, now let's talk about a little bit popular models that the people have been widely used today. Okay, so you can think about all these different graph neural nets, essentially a more advanced version of this simple graph neural nets in terms like a different aggregation function and update function. So the first one called the spectrum-based graph filtering. So the GCM method is a most representative method in this category. This is also a most cited paper in this domain. So the second group called the spatial-based graph filtering. This is very close related to the spectrum-based method, and most representative method called MPN, graph stage, and the GRN. We'll talk about the representative method later. And then attention-based method is also very popular. One of the most representative methods is called the graph attention network. So this is, I think it's the second most cited paper in this graph neural domain. And recurrent-based graph filtering called gated graph neural nets. This actually is the first modern graph neural nets that proposed before. Okay, so let's talk about the key idea of each category. So for the GCM method, the key idea here is try to apply a spectrum convolution on graphs, where they try to do a graph filtering process that is graph filtering operation multiply the graph signal. That essentially can be decomposed is the eigen decomposition with its graph signal. However, the graph eigen decomposition is very expensive. If a matrix, adjacent matrix A is large and dense, and therefore that later people try to accelerate that using chip shape polynomial. It's working well, but still not powerful enough. Later in the GCM paper, they derive this first order approximation from the chip shape polynomial. And although it's a very rough approximation, but I'm showing that it's already very powerful and also it's fast. But it's not stable. So therefore that later we also add this renormalization trick, to stabilize the numerical computation. GCN has been widely used in many NLP tasks, okay, like text classification, question answering, text imaging, topic modeling, and so on and so forth. So the second group is message parsing neural nets. The key idea here is that they try to cast a graph convolution as a message parsing process. For example, one of the most representative method called MPN. Essentially, they define two functions. One is called node aggregation function, and one is node update function. In the aggregation function, we take the node and the edge embedding as an input, and then to generate a message. And this message later will be combined with the graph node representation in the previous layers, and using update function to further update this. So this is a very generic learning framework that it can be used to unify many different graph neural variants. However, it's very expensive. As you can see, if the number of the nodes are large. So therefore, in order to accelerate this, we can apply some sampling technique. For example, to open some fixed number of the labels. That is the core idea that proposed in the graph stage. And so here, there are two merits about the sampling. One is try to reduce the computation. Other one is to reduce the overfitting. So this is also one of the reasons that the GCM method cannot be very deep. Typically, only 2 layers layer will be enough. That's because that you try to aggregate all the neighborhood. Okay, so therefore it's become very expensive. And for sampling based method, you are able to just sample a few of the neighborhood. Therefore, that you can greatly reduce the overfitting and increase the graph neural depth. So MPN and graph sage have been widely used for the knowledge graph, information transfer, and semantic parser. So GAT is another very popular variant in the graph neural domain. The key idea is very simple. So the previous methods, basically they treat all the graph nodes as equal important, but in reality it's not, right? Some of the graph node is more important to contribute to the current target node. Therefore, that it's very important to dynamically learn a weight or attention score on the edge, so that when we perform the message parsing. So once we learn the importance of each graph node, then we can perform a weighted sum of each node embedding. So in order to generate a final node embedding. So the idea of the compute this local weight is very similar to the transformer. Actually, this type of the multi-head attention score is also inspired by the transformer. Okay, and then later we can generate the final node embedding. So GAT have have been widely used for the many NLP tasks, text calculation, question answering, and so on and so forth. So finally, is the gated graph neural nets. So the key idea of this type of the graph neural nets is try to using gated recurrent unit while taking into account the edge type and direction. There are two key differences compared to existing method. One is that it's considered incoming, outcoming edges. Therefore, that it's not a simple adjacent matrix, augmented adjacent matrix. And the second thing is, so when they do the updating, they're using GRU unit to do the updating. So this is quite different from the existing method. And this method literally can deal with a directed graph, unlike the GCN and GAT that typically deal with undirected graph. Okay, that's almost all about the basic foundation about this tutorial. So next, we will talk about the key foundations of a DLG4NLP. We'll talk about the graph construction, where we'll talk about how to use the state graph construction method or using dynamic graph construction method to construct a graph from a text sequence. And then based on the graph we have been constructed, so what kind of graph representation learning technique we should use? That really depends on, so its graph is a homogeneous graph or multi-millionaire graph or hijack graph, because based on each of the graph type, we'll have a different corresponding graph learning representation technique for that. And after that, we'll talk about the encoder-decoder framework. That is one of the most popular variant in NLP domain and associated with many NLP tasks. We'll talk about gradual sequence model. We'll talk about gradual tree model. We will sharply touch the graph model. And finally, we will talk about all the different applications that have been introduced before. Okay, that's all for our roadmap for our DLG4NLP. Next, I will pass to Yu.
Thanks, Yingfei. Hello, everyone. My name is Yu. I'm a research scientist from Facebook AI. So next, I will introduce the graph construction for NLP. So let me share my screen. Okay. Yeah. First, let's talk about the graph construction for NLP. So as Yingfei introduced, like there are three typical ways of representing text, which are bag, sequence, and a graph. And among all the three approaches, graph has the strongest representation power because it can capture rich and diverse information about the text. And we also know that different NLP tasks require different aspects of the text, such as syntax, semantics. And in the meanwhile, different graphs capture different aspects of the text. So therefore, how to convert a text to graph is an important yet challenging question, which really depends on what aspects of information we want to capture in our text graph. In general, we group various graph construction approaches into two categories: a static graph construction and a dynamic graph construction. We will introduce each of them and summarize their properties next. So notably, the primary goal of the graph construction we are talking about in this tutorial is to achieve good downstream task performance. So let's first talk about the static graph construction. It aims to convert the raw text to a graph where text can be either like sentence, paragraph, documents, corpus, and so on. It's usually conducted during the pre-processing stage by augmenting the raw text with various domain knowledge, including like syntax, semantics, topics, co-occurrence, word knowledge, and so on. So many of them are actually quite application driven. The first static graph construction approach we are going to introduce here is the dependency graph. So dependency parsing is widely used to capture the dependency relations between different words in a sentence. For instance, given a sentence, are there other jobs outside Austin? One can apply dependency parsing tools to convert it to a graph like this. So, but like, what if we have multiple sentences in text? So one common way is to add additional sequential edges between nodes so that we can connect multiple dependency graphs in a paragraph. Besides, it can also reserve sequential information in the raw text, which can be helpful in some NLP applications. So next approach we will introduce is constitutive graph. The constitutive graph is able to capture phrase-based syntactic relations in a sentence, which is like different to the previous dependency graph, which can only capture like token-based syntactic relations. So for instance, given the same sentence, one can apply constitutive parsing tools to convert it to a graph. And due to the same reason, one can add additional edges, sequential edges between those nodes. So the AMR graphs are widely used to represent the high-level semantic relations between abstract concepts of text. Different sentences that are semantically similar may share the same AMR graph. Given a sentence Paul's description of himself a fighter, one can apply AMR parsing tools to convert it to a graph. The IE graph aims to extract the structural information from text to represent the high-level information about entities and their relations. So given the input text, one can apply IE tools to convert it to a graph, which contains entities such as Seattle's as nodes and the relations such as attended as edges. And the co-reference resolution is usually conducted to group entities referring to the same concept to a single node. For example, here like Paul, he and renowned computer scientist, like all these three nodes refer to the same person. So we can group them to a single node. The knowledge graph stores what knowledge about entities and their relations. Given a question, who acted in the movies directed by the director of Some Mother's Son? So one can first identify the top entity of this question, which is Some Mother's Son, and then extract a subgraph from a knowledge graph, which surrounds this topic entity and hopefully contains the answer entities of this question. Topic is a subject that the text is about, so one can find the connections among multiple paragraphs or documents by connecting them to a shared set of topics. So another way to find the connections among texts is to compute their pairwise similarity scores. And one common way to compute the similarity scores is to first embed the text into some vector representations such as TF, IDF vectors, and then one can compute their pairwise similarity in the embedding space. So in order to capture the word co-occurrence information, so one can regard the co-occurrence matrix as an adjacency matrix, and then construct a graph containing each unique word in the document as a node. So some logical forms such as a SQL query can also be naturally represented as a graph, which also can well capture the relations among various objects in the query. So there are also like various application-driven graphs which augment the text with rich information, and they are tightly coupled with specific NLP tasks. As we already seen, static graph construction operates by augmenting the text with various domain knowledge during the pre-processing stage, and these those domain knowledge include like syntax, semantics, topics, co-occurrence, word knowledge, so on and so forth. And for each type of the domain knowledge, there are various types of graphs we can construct, which usually depend on specific downstream application task. And as we will see in the application part of this tutorial, these static graph construction approaches are widely used in various NLP applications, such as information extraction, machine learning comprehension, natural language generation, text clustering, and so on. So next, we will introduce dynamic graph construction, which shares the same goal with the static graph construction. Unlike the static graph construction, which is performed during the pre-processing, dynamic graph construction operates by jointly learning the graph structure and the graph representation on the fly. And the ultimate goal here is to learn to optimize the graph structures and the representations with respect to certain downstream NLP task. So we summarize the typical dynamic graph construction pipelines as follows. So given a set of data points, which can stand for various NLP elements, such as words, sentences, and documents. So we first apply graph similarity metric learning, which aims to capture the pairwise node similarity and returns a fully connected weighted graph. Then we can optionally apply graph specification operations to the fully connected weighted graph in order to obtain a sparse graph. And if the input data is instead of data points, but an intrinsic graph containing edges, we can also optionally combine the intrinsic graph and the learned implicit graph to form an augmented graph. And the output graph will be consumed by a subsequent GN-based module to learn graph representations and predict outputs. So next, we will introduce each of the 4 dynamic graph construction techniques, which we summarize from the existing practice of its applications in the NLP field. This include graph similarity metric learning techniques, graph specification techniques, combining intrinsic graph structures and implicit graph constructions, and various learning paradigms for dynamic graph construction. So the idea of graph similarity metric learning is to compute the pairwise node embedding, node similarity in the node embedding space, and obtain an adjacency matrix based on that. It can enable inductive learning because once the similarity metric is finished, one can apply it to unseen nodes to learn a graph. This is important for many NLP applications because we want to learn a new graph for each new text example. So various metric functions have been proposed by previous works. And we group them into 2 categories. One is node embedding based similarity metric learning. And the other is structure-aware similarity metric learning. Next, I will introduce each of them. So for node embedding based similarity metric learning, we are given a set of data points and their vector representations. And we want to apply various metric functions to learn a pairwise node similarity. And its output is a weighted adjacency matrix, which is corresponding to a fully connected weighted graph. And common matrix functions include attention-based and cosine-based functions. So let's first talk about attention-based similarity metric functions. So here we can, yes, we see one variant of such a metric function. So in this variant, V1, Vi here is the node embedding, and the UI is a non-negative weight vector, which learns to highlight a different dimension of the node embeddings. And here, U has the same dimension as the initial node embedding Vi here. And in the second variant, here W is a learnable weight matrix, which maps the node embedding to a latent space. And the value function is used here to enforce the sparsity of the learned matrix. So as we can see, in both of these 2 variants, the dot product is used to compute the similarity. Let's see an example of cosine-based metric function. So here, WP is a weight vector associated with the piece perspective and has the same dimension as the node embeddings. So intuitively, SIJP here computes the pairwise cosine similarity for the piece perspective, where each perspective considers one part of the semantics captures in the node embedding. And one can average multi-head similarity scores to increase the learning power of the metric. So this is kind of similar to the idea of multi-head attention in the transformer models. Now let's talk about the structure-aware similarity metric learning functions. So unlike the previous mentioned the node embedding based metric learning, this metric learning approach, in addition, considers the existing edge information of the intrinsic graph when it's available. So let's see 2 example metric functions belonging to this type. So in these 2 variants, attention-based function is applied, and notably, the edge embeddings of the intrinsic graph play an very important role in learning the implicit graph structure. So far, our similarity metric functions is able to learn a fully connected graph. However, a fully connected graph is computationally expensive and also might introduce noise. So we might want to enforce sparsity to the learner graph structure to obtain a sparse graph by leveraging variance techniques as what we list as follows. So let's see a few graph specification options which are commonly used in previous literature. So first is the K style specification. For this type of approach, for each node, only the K nearest neighbors, including the node itself, and their associated similarity scores are kept, and the remaining similarity scores are just masked off. And for epsilon neighborhood specification, those elements in the similarity matrix S, which are smaller than a non-negative threshold epsilon, are all masked off. So besides explicitly enforcing the sparsity of the learner graph by applying certain form of threshold, like either the K or the epsilon, which we introduced, sparsity can also be enforced implicitly in a learning-based manner. For example, we can apply certain form of graph regularization to the learn adjacency matrix to enforce sparsity implicitly. So the intrinsic graph typically still carries rich and useful information regarding the optimal graph structure from the downstream task. So some recent works proposed to combine the learned implicit graph structure with the intrinsic graph structure based on the assumption that the learned implicit graph is potentially shift from the intrinsic graph structure, which is supplementary to the intrinsic graph structure. So one common way to combine the benefits of the above two graph structures is to compute a linear combination of the normalized graph Laplacian of the intrinsic graph structure and the normalized adjacency matrix of the learned implicit graph structure. So, and then we can we can apply like variance normalization operations to the learned adjacency matrix, such as graph Laplacian or like non-normalizations. So as a result, so both the information captured in the intrinsic graph structure and the additional information learned by the dynamic graph construction can be utilized in order to learn a better graph structure for the downstream task. So now let's talk about some important learning paradigms for dynamic graph construction, which have been explored so far. So the most existing dynamic graph construction approaches for GNNs consist of two key learning components. The graph structure learning component and the graph representation learning component. So the most straightforward strategy is to jointly optimize the whole learning system in an end-to-end manner towards the downstream prediction task. So another common strategy is to adaptively learn the input graph structure to each stacked GNN layer to reflect the changes of the intermediate graph representations. So this is kind of similar to how transformer models learn different weighted fully connected graphs in each layer. Unlike the above two learning paradigms for dynamic graph construction, so recent works propose an iterative graph learning framework by learning a better graph structure based on better graph representations. And in the meanwhile, learning better graph representations based on a better graph structure in an iterative manner. So as a result, this iterative learning paradigm repeatedly refines the graph structure and the graph representations towards the optimal downstream performance. And variance stopping conditions can be applied for the iterative learning process here. For example, one can stop the iterative process when the difference between the learned adjacency matrix at consecutive iterations is small enough, so which is the stopping criterion, stopping condition used in the original paper. So far, we have introduced variance dynamic graph construction techniques including graph similarity metric learning, graph specification, how to combine intrinsic and implicit graph structures, and also variance learning paradigms. So one might ask, like, how is static graph construction compared with the dynamic graph construction in the NLP field? Like, which one is better? So let's first talk about the static graph construction. So the biggest advantage is for the static graph construction is that it can like very easily encode rich prior knowledge in a graph. This can be very helpful for certain NLP applications, but this can also become downside when it's expensive or it's not practical to obtain such extensive like domain expertise. For example, for some low resource languages, we might not have rich prior knowledge to utilize. Like we might not be able to obtain very high quality like dependency graph or AM graphs. So, so besides a static graph construction is also error prone due to the noise or incomplete graph, and therefore is often suboptimal. And due to its disjoint graph construction and the representation learning nature, it can also lead to error accumulation. Like for example, if we do not have very reliable prior knowledge, then we might not be able to construct a high quality static graph. Then the error introduced in the graph construction stage can be can lead to the overall poor performance of the whole system. So compared to the static graph construction, dynamic graph construction is actually quite new and has not been extensively studied in the DLG4NLP area. So its advantages include requiring no domain expertise, and it jointly learns the graph structure and the graph representations in an end-to-end manner. And currently, it also has some disadvantages such as the scalability issue and the lack of explainability. But these are also two like active research directions for this dynamic graph construction topic. Now it comes to the question, when to use which. So based on our study and practice, it's best to use static graph construction when we have domain knowledge at hand, which fits well the task and can be represented. And the domain knowledge can be easily represented as a graph. For dynamic graph construction, there might be some reasons why we want to look into this approach, which include, like for example, one, there's lack of domain knowledge which fits the task or can be represented as a graph, or the domain knowledge we have is incomplete or might contain certain noise. And or we want to learn an implicit graph which augments the static graph constructed based on the prior knowledge we have. I think the third point is really promising because in many cases, in some NLP applications, we do have some prior knowledge to utilize, and we do not want to totally discard those useful domain knowledge. But sometimes the domain knowledge might not be that perfect. So in this case, like we can try to leverage the dynamic graph construction to learn an implicit graph which augments the intrinsic graph, and as a result, we might be able to learn a better graph structure which is optimal for the downstream prediction task. And the good thing is that we can do this graph structure learning in an end-to-end manner. Okay, so that's for graph construction. Now let's move to the graph representation learning for NLP. So let's first briefly recap on the DLG4NLP pipeline. So given a graph which can be constructed either using like a static graph construction or dynamic graph construction approaches, we will need to decide which GNNs to apply for the graph representation learning part. And this is actually a big question, and we will try to answer this question in this part of the tutorial. So let's first review some definitions on various types of graphs. So typically we can categorize like graphs into three types. One is a homogeneous graph, which contains only a single node type and a single edge type, which is quite simple. And the multi-relational graphs is a class of graphs which contain more than one edge type, and it only contains like a single node type. And a heterogeneous graph is a class of graphs which can have more than one node type. So these concepts are important here because we will mainly depend on the graph types to choose which genes to apply. So let's first see the overall roadmap on which genes to use given a graph. So this works like a decision tree, which we summarize to help you make this decision about like which gene to use given a graph. So in short, we will decide whether to apply homogeneous genes, multi-relational genes, or heterogeneous genes based on the input graph types. So in the next few slides, we will introduce each of the three scenarios specifically. So first, let's talk about the homogeneous genes. So when to use homogeneous genes? So given a graph, if it's a homogeneous graph based on its definition, then we can definitely apply a homogeneous graph. Or it's not a homogeneous graph, but in order to apply homogeneous genes, we can choose to convert the input graph to homogeneous graphs by leveraging some techniques, which we will introduce next. So once we get a homogeneous graph, and we can simply apply homogeneous genes, which include like GCN, GAT, GraphSage, and the GGN. So most of the earliest versions, GN variants are like all belong to homogeneous genes. So now let's talk about how to convert non-homogeneous graphs to homogeneous graphs so that we can apply homogeneous genes. So one common way to do that is via Lavie graph conversion. So the key idea of Lavie graph conversion is to regard each edge in the original graph as new nodes and connect the original nodes and the new nodes. So as a result, we will get a bipartite graph, which contains the original nodes and the newly added edge nodes. Okay, now let's talk about how to handle edge direction in the graph. So we know that edge direction is important. Just think about the success of BiASTM and the BERT models. So they all will capture the direction information of the text. So given a directed graph, we might not be able to directly apply some homogeneous genes, which will lead to like edge direction information loss. So common strategies for handling directed graphs include one, we do message passing only along directed edges, but this is not ideal because we will have edge direction information loss. And the second strategy is to regard edge directions as edge types. Then we get multi-relational graphs. Then we can apply multi-relational genes to encode the information. And as a third approach, we are going to introduce here is bidirectional GNNs, which can naturally handle directed graphs. So in the next few slides, I will introduce the second and the third strategy specifically. So for the second strategy, which is to regard edge directions as edge types. So this is actually quite straightforward. The idea is to just simply like regard edge directions as edges. Then we can convert a directed graph to a multi-relational graph. So as a result, we can have three types of edges. One is the default edge, which include the original edges in the in the original graph. And we can also have inverse edges and the self edges. So the self edges means the self loops. We can add self loops edges for each node. So by doing that, we can use we can apply multi-regional GNs to encode the edge direction information. And the third strategy is to apply bidirectional GNs for directed GNs. So bidirectional GNs is a class of GNs which are specifically designed to better handle better encode the edge direction information. We summarize like two variants of bidirectional GNs. The first one is called the bicep GN. So the bicep GN works very similar to the very famous BiLSTM model, as we will see very soon. So firstly, for bicep GNs, we will first run multi-hop backward and forward GNs on the graph for the incoming edges and outgoing edges separately. And we do this, we run this like multiple hops. Then we get backward node embeddings at the forward node embeddings at the last hop of the GN. So once we get these two node embeddings from two directions, we can simply concatenate the two node embeddings to get the final node embeddings. So as you can see, like this is very similar to how BiLSTM models work. So the next variant of the bidirectional GN I will introduce here is called the bifuse GN. So for bifuse GN, we will first run one hop backward and forward node aggregation. As a result, we can get aggregated node embeddings from both incoming edges and the outgoing edges. Then we also fuse the two node aggregation vectors, but we do that at each hop of the GN. So there are many ways to fuse the information. Like for example, we can use the gated recurrent unit to fuse the backward and the forward aggregation vectors. So once we get the aggregated node embeddings, then we can use that information to update the node embeddings at each hop of GN. Then we can still like stack multiple GN layers, and at each layer we just repeat this. So as a result, we can get this bifuse GN variant, which can naturally handle the graph direction information. So let's move to the multi-regional GNs for NLP. So when to use multi-regional GNs? So given a graph, if it's not a homogeneous graph, and also like if we don't want to convert it to a homogeneous graph and it contains only one node type, then we know that the graph is a multi-regional graph. Then we can apply multi-regional GNs to learn the graph and the node embeddings. And also like and another way to scenario is that like if it's not a homogeneous graph and we want to but it's a directed graph, and like remember that we previously introduced that we can regard the edge direction as the edge type information, which will result in like a multi-regional graph. So in this case, we can also apply the multi-regional GNs to learn the embeddings. So these are typical scenarios where we want to apply multi-regional GNs to learn the embeddings. So as for multi-regional GNs, there are many variants. So specifically, we will introduce like three typical variants of multi-regional GNs in this tutorial. One is to include the relation-specific transformation parameters in GN, which we call it like RGN, relational GN. And as the second strategy is to include edge embeddings explicitly in GNs. So so remember that in many GN variants, actually the edge embeddings are not explicitly introduced in the metric parsing process. So here we can we can explicitly introduce the edge embeddings in the GNs in order to better handle the edge type information. And the third strategy is, we call it like multi-relational graph transformers, which combines the benefits of both the vanilla transformer models and the traditional and the conventional GN models. So we will talk each of them in the next few slides. So let's first talk about the first strategy, which is the relational GN. So the RGN is the most common variant, which works like this. So it has two features. One is to introduce a relation-specific transformation, as we can see from this from this equation. Like here, the RK is the relation-specific transformation parameters, and R respects to the relation type. So that means for each type of relation, we will introduce a learnable model parameter. And the second like a property of RGN is it aggregates information per relation-specific subgraph. So we have here we have a diagram to better illustrate this idea. Okay, so one particular variant of RGN is RGCM model. So it introduces the relation-specific node feature transformation during the node neighborhood aggregation process for the GCM model. So as we can see here, WRK is the relation-specific D by D learnable weight matrix, and we have this W for each relation type R and for each GCM layer. So as we see from the previous equations, RGN is good at doing relation-specific message parsing, and hence it can handle multi-relational graphs well. However, it's sort of expensive because we needed to introduce the learnable parameters for each relation types, and for some large-scale graphs which contain a large number of edge types, this is quite expensive, and it might lead to overfitting issues. So how to avoid this over-parameterization? So there are two common ways. One is to introduce the basis decomposition, which regards the relation matrix as a linear combination of some shared bases. So this can be seen as a form of weight sharing between different relations. And the second strategy is called block diagonal decomposition, which can be seen as a matrix sparsity constraint. So both approaches can help kind of alleviate this over-parameterization problem of the RGN model. Okay, now I will introduce the second strategy for second type of multi-relational GNs, which operates by including edge embeddings explicitly in the message passing process of GNs. So so here in this specific variant, we can see that the edge embedding EIJ is actually participating into the message passing process, and in variant 2 here, EIJ also participates into the message passing process. And additionally, here we also updated the edge embeddings at each hop of the GN. So this is slightly different from the variant 1. But in both variants, the edge embeddings, we introduced the edge embeddings into the message passing process. Okay, now let's talk about the third type of multi-relational GNs, which we call it a multi-relational graph transformer. So as we know, transformers can be regarded as a very special class of GNs where multi-head self-attention is learning dynamic graph structures adaptively at each layer. And it also, transformers also share many similarities with the graph attention networks as mentioned by Lin Fei. But one drawback of the vanilla transformer model is that they fail to effectively handle arbitrary graph structured data. So in many applications of transformer models, the input is regarded as like a sequence of tokens, and the positional embeddings is introduced in order to encode the sequential information of the raw text. However, for some input data which is not a sequence, it's better represented as some graph structures. Like transformers might not be a good, might not be an ideal tool to learn their representations. So, however, GNNs are a very natural choice if you want to encode the graph structured data. So here, multi-relational graph transformers try to combine the benefits of both the transformer models and the GNN models by introducing two specific features. One is to employ the structure-aware self-attention mechanism. And the second feature here is it respects variance relation types in order to better handle the multi-relational graphs. Okay, so let's see two specific variants of the multi-relational graph transformer models. But the first variant we see here is the RGAT-based graph transformers. It has two features. One is that it introduces the GAT-like master attention mechanism. So as we can see from this equation, so this is slightly different from the self-attention mechanism introduced in the vanilla transformers, because here we introduce a mask matrix to respect the graph structure of the input data. And the second feature here is it introduced the relation-specific learnable weight matrix. So this is kind of similar to the here the idea is similar to the RGN model. So that's why we call it RGAT-based graph transformers. And the second type of multi-relational graph transformers is we call it structure-aware self-attention-based graph transformers. So as we can see here, in order to respect the graph structure of the input data, here we introduce the edge embeddings to the self-attention mechanism of the vanilla transformers. So as a result, the model can better utilize the graph structure information of the input data. So next, let's talk about the heterogeneous GNNs. So when to use heterogeneous GNNs? So if given a graph, it's not a homogeneous graph, and we don't want to convert it to a homogeneous graph, and it contains more than one node type, then based on the definition, this belongs to a heterogeneous graph. Then we can apply heterogeneous GNNs to learn the representations. So in this tutorial, we will introduce one particular type of heterogeneous GNNs, which we call it Metapaths-based heterogeneous GNNs. So let's first talk about what is the Metapaths. So Metapaths is a very commonly used concept in the topic of heterogeneous graphs. So here's an example of Metapaths. So given and also know the type pair here, we can extract at least two Metapaths between them. For example, we have an author who writes a paper, and the paper mentions a topic, and that topic is mentioned by another paper, which is written by another author. So following this logic, we can construct a Metapath, which is author, paper, topic, paper, author. But we can also figure out some other Metapaths between the author node type. For example, an author can write a paper which is published by a certain venue, and as a venue also publish another paper which is written by another author. So as a result, we can construct a Metapath, which is author, paper, venue, paper, author. So as you can see, given a certain pair of node types, one can construct a variance metapath, which can capture the kind of the relations between certain pair of node types. So based on this metapath idea, researchers have proposed many metapath-based heterogeneous genes in order to better learn the representations of the heterogeneous graphs. So one example is called the HAN model. So it can be conducted in the following 3 steps. In the first step, we can introduce the type-specific node feature transformation. So as you can see, for each node type, we introduce the specific learnable weight matrix, which can map the node embeddings to some shared node embedding space. In the second step, we can do node level aggregation along each metapath. So as we can see from this equation here, we aggregate over neighboring nodes in every case metapath. And in the third step, we can do metapath level aggregation. So here we learn a weight attention weights over all the metapaths, and we do the aggregation here. So that's for the heterogeneous students, and that concludes the graph representation learning for NLP part. And thanks. And now let me pass it to Lindsay to talk about the graph encoder decoder models for NLP.
Okay, thank you. Okay, let's continue to talk about graph based encoder decoder model for NLP. So here's some basic background about sequence. I don't know how many people have been using a sequence model for some of the applications that you are dealing with. Basically, the sequence model is a very successful model, have been proposed around 2014 by tackling the problems that have sequence input and have sequence output. Originally, it has been proposed for the machine translation. For example, to translate English to French. But later people found that this type of learning framework is very useful for other tasks as well. For example, natural language generation, natural form, translation, information extraction. So although despite the great success of the sequence model have been achieved, there are several challenges associated with the model. First of all, so it's only applied for a problem that the current input is represented as a sequence. But in reality, the input could be much more complex. For example, the graph that we have been talked about so far. So if we want to leverage, for example, any kind of problem that have a graph input, then you have to convert the graph to the sequence, then you will lose information. Another important thing is that, so in just as we, as you mentioned many times, right, we have many ways to construct a graph. So that is good because we try to augment the original text sequence with additional structure information. That will enhance what the sequence feature. So for that, it's very important to propose a new model so that we can deal with the complex structure input and then have a sequence output. So motivated by this observation, so we have been proposed this gradual sequence model back to 2018. And also have a further improvement in IJCAI 2020. So here's a key idea for this gradual sequence model. We have this graph encoder model. We have this sequence decoder, and also we have attention so that we can help the decoder by attending the important node in the input side. So in the graph encoder, it's not only to consider a simple graph neuroness. Instead, we are considering this bidirectional graph neuroness variant that have been introduced by you before, actually. So here's some basic the graph formulation that you have been talking about. So it's very important because the graph we have been dealing with is not guaranteed that it will be an undirected graph. It could be a directed graph. So in this case, so we want to emphasize the importance of the directions by splitting them into incoming edge and outcoming edge. Therefore, that we can have this backward and forward GM, and we compare them together, so we will get a better node representation. So other one is bifuse, similar idea, but instead of to calculate the node representation at the end, we will fuse the information in the intermediate step so that we can have a better representation each step. Okay, so once we have the bidimensional node representation, we need to get a graph level embedding. There are basically two ways to get that. One is called pooling-based graph embedding that have been introduced before. We call it a flat pooling method. You can use either like maxing pooling, min pooling, average pooling to get a single vector to summarize the whole graph. You can also have this called a node-based graph embedding. The idea is that you can add a super node that can connect to all the graph nodes in the current graph, so that you can run the graph representation learning algorithm as before. And finally, you are using the embedding of this super node as a graph level embedding. However, the problem is that so you arbitrarily insert a new node into the original graph, you will destroy the original or bring noise into the original true graph topology. Therefore, that have been observing that so the pooling-based graph embedding typically will perform better than node-based graph embedding. So the attention is very important. You have been using sequence before. Without attention, the sequence decoder will harder to generate a token that is highly related to the input side. So attention will help us to emphasize to the most important part so that we can associate with the input side to generate the token that is focused on the important part. So the objective function will be like we try to maximize the local likelihood of the current probability by generating a current word token, giving the text sequence, the previous generated one, and the text sequence. So here's some tasks that have been evaluated this graph-based graph sequence model. So in the left-hand side, it's called the baby task. So this is only proposed by Facebook AI. Try to test all the current deep learning model for the reasoning capability. So in this, they have a bunch of the text, original text information, and essentially how to understand this text context so that you can answer the question well. So, so in the other side, we also try to test on the pure graph topology for the shortest path problem. You have destination, you have a target position, and you try to find the shortest path between them. So as you can see that so the graph-based method definitely will perform better on the LCM-based method, and our bidimensional graph sequence perform better than other graph neural nets. So here is a more deep understanding about effect of the bidimensional node embedding. As you can see that so within bidimensional graph, it's about converging much quickly. That is quite easy to understand because we're trying to learn the representation of both sides, incoming and outcoming, compared to unidirectional node embedding. But no surprisingly, that so finally, so when you have a large enough hops, they will finally have a very similar performance. That because that eventually you will reach learn all the content information about the graph. Therefore, that whatever is bidirectional or unidirectional, they will have very similar performance. So okay, so when shall we use graph sequence? So in the case one, that is more like your input is already naturally represented in graph or best represented in graph. Give an example. So in NLP domain, I have a task called AMR to text. Essentially, giving an AMR graph, we should generate a text description to describing the AMR graph. So in this case, you can see that so it's very natural to use our graph sequence because your input is already in graph format. You want to keep the original input and using a graph encoded to linear representation, and then to do the text generation. But the other case that so we have been using many ways trying to augment the current sequence to generate a hybrid graph with this hidden information. So in this case, so you essentially try to leverage additional information for the text sequence so that you can gain more information. In this case, you should also use a graph sequence. Right now, you already have a graph input here, and you try to make full use of this information. Okay, so beyond the learning and mapping between a graph structure input and sequence output, many other NLP applications even go further. That you try to learn a structure input and structure output, showing these two different applications. One is a semantic parser, other one is math word problem. I can see that so the text input can be wrapped as a graph, as we discussed many times before. And the output here, it could be some logical form, or could be some math equation. And you can see that essentially they don't really, it's a sequence. It's have a very special structure for me, organization, so that it's better to treat them as a more complex structure, for example, a tree structure or graph structure. So in this case, we are trying to propose a more complex learning framework called the gradual tree model. Essentially, we need to convert the input as a graph and with augmented hidden structure formation, and also to cast the sequence output as a tree output, so that it can better preserve the original structure information. So they typically have two different tree decoding. One is DFS-based tree decoder, and one is BFS-based tree decoder. They both have advantages and disadvantages. In our current framework, we are based on the BFS-based tree decoder. So this is a whole architecture model for our gradual tree model. So you have this input, and we are using dependent part tree to augment original input, and we can try this hybrid graph. And then we use the bidirectional representation, try to generate graph level representation, and then we send to a tree decoder. And in tree decoder here, we are also have this beyond the pattern fitting, we also have this symbolic fitting in order to better to leverage the existing decoder information. And more importantly, we have this separate attention instead to have this homogeneous attention. That's because so this really depends on your graph type. If a graph is a heterogeneous graph, that means that so the different node may have a different type. For example, in this case, so one type of node is from original word token, another one is from the dependency parser. And in this case, we can have a separate attention to learn the importance for the different graph node, so that we can compare them together to finally get the better context vector. So this is basically the math behind what we are describing for this separate attention. And so this is a result when we evaluate on the math word problem. And I can see that so our gradual tree model perform much better than current state of art. One thing I want to emphasize is that so the most state of art using this equation normalization technique. This essentially try to break all the different diversity of the thinking to create a math equation when you try to read the math word problem. So it will definitely will improve the learning capacity, but it's also will destroy the original reasoning process, because when you try to recover how the student reasoning this problem, you cannot really recover the original equation. And in our gradual tree model, we firstly keep the original math equation, so that we can firstly to regenerate the math equations. I think this is very important. The second part, we also evaluate on other math equation data set, and we have a very similar result. And here's some visualization about a separate attention. We can see that interestingly, so indeed the attention will help us to find the important the input token associated with the output, so that we know that so indeed so our separate attention is capture the most important information. Okay, I think that's all for our first part, our DLG4NLP tutorial. So we will have a 10-minute break, and here is some demo that we're going to show later after introduce our applications. And so please bear with us, and we will resume our DLG4NLP tutorial in 10 minutes. First, we'll talk about application, and then demo, and then we'll conclude this tutorial. And if you have any question, please feel free to post in chat, or you can also unmute yourself to ask a question. Okay, we will resume in about 2 minutes. Okay. Professor Chi, do you want to share your screen instead?
Yes. Give me 1 second.
Sure.
Can you see my screen okay?
Yeah.
Okay, awesome.
Okay. Yeah, please feel free to start at 11:35.
Sure, thanks. Okay, so I think we can start. Welcome back. And this will be the first application session about how to use the algorithms and you have described before and to a series of NLP applications. So information ingestion is probably the most natural application of this kind of graph algorithms because the goal of information ingestion is to convert a sequence to graph. So I'm going to talk about some new algorithms using graph learning for event ingestion and for relation ingestion. And then I will talk about how to improve the quality using this kind of algorithms and then improve portability, means that how can we do cross-lingual, cross-media transfer. And then finally, I will talk about some new directions using graph schema for improving the quality and do event prediction, and then finally apply it to missing information detection. So IE is a sequence to graph task. Basically, we can take a natural language sequence, either in a paragraph, sentence, or corpus as input, and then we want to get the information graph. In each graph, you will see every node could be an entity or a trigger for the event. And then we can find the relations between entities and argument roles this entity played in the event. So the modern deep learning methods for this task usually will encode every token in the input sequence. So we will do sequence encoding. For example, you can use BERT embedding to represent every token. And then we try to do bin search to decode a graph out of this. So there are several problems for this framework. The first one is that we are limited to sentence level because it's usually too time consuming and there are too many candidates if you apply this to the whole paragraph or even a document or corpus. And the second is that there are many pre-processing NLP tools available, such as semantic parsing. So we should be able to take advantage of them so that we can capture wider local context. So there are some recent work try to attempt this kind of idea by trying to convert sequence to graph to graph. So the idea is that let's wait a little bit to encode the sequence. We are going to using semantic parsing or just construct a span graph using transformer so that the input will be as well. And then we can use graph encoding to replace the sequence encoding. And then also we can do graph guided decoding rather than bin search. So this is our this year's paper that will try to implement this idea. So the encoding part will use a semantic parser. And for example, one semantic parser is AMR parser. Lin Fei has already talked about it. So abstract meaning representation AMR parser can extract more than 100 types of relations. And then from this graph, we can encode the tokens and entities using the graph context. So for example, initially in the input sentence, maybe this trigger and this entity are far away, and now they are only one edge away. And then in the decoding part, we are going to look at every trigger identified from the input sequence or input graph. And then we'll look at the subgraph covered by this trigger word to find the arguments, rate arguments. So we call this as graph-guided encoding and decoding. In the encoding, you can try to also use attention network, because in that way, different edges types will have different weights. So we use edge conditional GAT to use incorporate information, propagate the information from the neighbors to update the encoding for every node in the graph. In the decoding, instead of going from left to right, like in the bin search, we're going from top to down for every node that indicate a trigger. So basically, for example, if here we already identify this red node as a trigger for a certain event type, we're going to look at these three nodes that are being covered by this red node and search for the candidate arguments. So the biggest advantage is that we are able to capture wide context. For example, here, the airlifting is trigger word and Washington is argument. They are far away in the input sentence, but they're only one hop away in the AMR parsing output, so that we can identify this Washington as argument. And in the original sequence graph model, we fail to identify this argument. So that's about improving the quality when you do have a resource available, for example, for English news. But in reality, in many cases, we don't have so many resources or training data, for example, for some foreign languages or for images and videos. So I'm going to talk about how can we use the graph learning to do structure transfer. So in the NLP community, cross-lingual embedding and use that for transfer is not new. There are tons of work about using cross-lingual word embedding and then do token level transfer. So the goal here is not to do a sequence transfer, but rather we want to do structure transfer, because relations and events are involving multiple tokens, multiple entities. So it's really about how can you transfer the whole graph structure. And the good news is that across languages, we often find the graph structure that captures certain relational events are always identical. So for example, here, if you look at the universal dependency parsing output for English and Russian, even though these two sentences are not parallel, but if you look at the same type of relations connecting the pink node and blue node, the paths look identical. So which means if we can train a model from English, and since these structures are identical, we can simply apply this model to any other languages, as long as you can encode the node in these two graphs using the common semantic embedding space. So we are going to initialize the node embedding using multilingual word embedding, and then use graph convolution network to update the node representation. So the idea is very simple. In each previous layer, you will have the initialized embedding, and in the next layer, we're going to propagate the embedding from the neighbors to update the counter node embedding. So for initialization, in addition to multilingual word embedding, you can also try to use any language universal output which is available for these two languages. For example, some languages may have the same speech tag, or maybe there are some anti-injection tools available, or maybe universal dependency parsing is available. So you can put them together to initialize the representation. And then for any IE task, we can simply consider this as a classification problem. So for example, we already identified a trigger and entities. Now the classification task is trying to identify whether this entity mentioned is the argument for the trigger. So that means if we have some training data for English, we can first encode the training sentence and the test Russian sentence into the same common space, and then you can train a model to classify the relation between the pink node and the blue node, for example, and then we apply that to the Russian sentence. So using this kind of model, we are able to achieve similar performance compared to a supervised model that was trained from more than 3,000 event mentions. So that means this kind of structure transfer can save a lot of annotation cost. All right, so that inspired us. Maybe we can also use this kind of idea to do structure transfer in a cross-media setting. The reason is because although we have a lot of annotation and training data available for English news text, but for news domain, we don't have such rich resource or training data for images and videos. But it's really important to find information from multimedia, because we found more than 33% of the arguments of events actually only coming from images or videos in a news article. So the task here is not just try to convert this natural language into a knowledge base or into a graph, but we want to get the information from images as well. So for example, here, two vehicles, they are only presented in the image. So we want to populate this event table by merging these arguments. So like I said, because we're lacking the training data for images, the goal here is to merge the image representation and this sentence representation into one common space. So the idea is very similar to what we have already seen in English and Russian in the sample. The only difference is here we are considering this image as another foreign language. So fortunately, in the computer vision domain, they already have all kinds of semantic parsing equivalent tasks. For example, situation recognition, which can give us the verb that showing the main event in each image, and also the corresponding semantic rules showing the bounding box associated with this verb. So that means we can convert every image into a semantic graph, which will be similar to the semantic graph we usually get from the text side. So we decided to gather together all the image and caption pairs we collected from 15 years newspaper to construct this common semantic space. So one thing I want to note is that because of the limitation of the vocabulary used in the object detection algorithms, we want to be able to cover all the bounding boxes that indicate important arguments. So here we also apply attention map, cross-media attention map to identify some implicit arguments in the images. Okay, so now after we have this semantic graph, they serve as a bridge to connect it to different data modalities. So for example, here, this bounding box will look similar to protester, and this one will look similar to another vehicle you normally see in natural language. And then if we have trained data from the two data modalities, we can merge them together using this common space, and then we can train a joint model. This joint model can be applied to any multimedia news article in which the image and the body text, they don't have to be well aligned. And then we can apply this to all kinds of IE tasks. So we are trying to compare this with the single data modality models. For the left image, you can see that if we don't have very powerful facial recognition, facial expression recognition system, we will fail to identify the event type for this image. So we may mistakenly identify this as a protest. But the text, body text tells us this is about a ploy, a very happy ploy, so we can fix that event type. Similarly, if we don't have the image facial features, then we only look at the text side, we may miss the arrest event here because search is not a very common trigger word. But looking at the common semantic embedding space, we are able to infer this is an arrest event because of the structure information in the image. So again, similar to multilingual embedding, there's a lot of work on multimedia embedding, but they usually only look at the word level and the pixel level or region level alignment. They ignore the structures. So compared to those kind of methods, our model is able to find the roles. For example, here, this person was mistakenly identified as agent in the flat model, which ignore the structure transfer, and we are able to identify this person as a person who is being arrested. And this kind of method works particularly well when you have a very big crowd that serve as one role for a certain event, such as the right image. Okay, so this kind of algorithms not only improve the portability, but also quality. And now I want to also talk about the new directions, new future research opportunities graph learning algorithms bring to us. So the first future direction is to extend our scope of extraction from sentence level to the corpus level. Because history repeats itself, so you'll see repeated events again and again in a lot of historical data. So it will be good to learn patterns and schemas from this kind of large amount of historical data, and maybe we can encode that as a global features to improve IE performance. And maybe we can even predict what's going to happen tomorrow. So event schema will look like this. It's a hierarchical structure. For example, here, the scenario is about silver unrest. You will see lots of sub-events. And then among the sub-events, you will see causality and temporal relations connecting them. They are also sharing lots of event arguments. So how to do this kind of schema induction? Again, we are going to use graph algorithms. The first idea is to look at every pair of events, and then you can simply check all the multiple paths connecting these two nodes. And then we can rank these paths based on salience and coherence. So salience is similar to path language model. You can just mask out some nodes and edges and count their frequency. And the coherence measure is to look at two neighboring paths in the graph to check how likely they co-occur in the same news article. So by ranking the paths, we will be able to find which one is most salient and coherent and put them into a schema. So their path language model training is very similar to what we normally see in autoregressive language model training. And we also capture co-occurrence of two paths for coherence measurement. And then we can translate the top ranked paths into some global features. For example, here in the original sentence, there's an entity and another destination. This entity reached by this movement event, but the input sentence is lacking the context to tell us that's located in relation. And our path language model will tell us these two are top ranked paths connecting these two events, and there's a located in relation between these two entities. So use that, we can infer this relation. Once we apply this to every component in the IE pipeline, we can see that we can achieve significant improvement, especially for event and relation injection. So we want to extend this further to capture all the possible events, not just every pair of events in the whole graph. So for example, here we're showing a IED scenario in which this person learned how to make a bomb, and they assembled the bomb, and they moved to a place, and there was a explosion event, and then some damage and dying injury event happened right after that. So all of these events are also sharing lots of entity arguments, and they form a graph structure. And we'll see the similar patterns again and again in the historical data. So maybe we can just simply learn a graph generation model. And also on top of these flat graphs, we can also learn hierarchies. For example, we can segment this scenario into multiple episodes. Each episode will have a sequence of events or a subgraph of these events. So if you
let me mute all speakers. Professor G, could you unmute yourself? Yeah.
Thank you. Yeah, so the graph generation model simply starts from a very small graph. For example, we already inject a tag and die event from the input document, and then we will predict what is the next event. So arrest is the next event node. And then we are going to predict what is the most probable edge that link these two nodes, or what is the path link them. For example, they are involved in sharing arguments, or their arguments are related. And then finally, we are going to determine the temporal relation, whether this arrest event happened before or after die. So that's the whole idea. And then use this kind of a graph generation model, we not only can induce schemas, but we can also apply that to do event prediction. For example, this subgraph is what we already observed or extracted from the current documents, and we can predict these 5 new events that will follow after this. So we also compared the performance with using human schema. So human schema has 2 big disadvantages. Number one is it cannot give you accurate probability distribution. Second is that it does not really look at the connections between multiple hypotheses. So it will also mistakenly predict some very popular event types. For example, here, trial hearing and a sentence, this person was not arrested yet. So these 2 are errors, but our model can predict not only the accurate events, but also reliable confidence and the probability distributions. So you can see the accuracy is much better than the model using human schema. All right, so because we can also construct hierarchy, we can also extend this to episode prediction. For example, we can predict the whole episode after this investigation, and these 3 nodes and their parent node will be predicted automatically. And we can also propagate the event arguments from their previous events, so that we can even predict who is involved in their future event and what role they are playing in the future event. And of course, you can also go back to look at the historic events. You can also predict some missing events in the old history. So that's the whole idea for event prediction. And then finally, I want to also briefly talk about another more exciting application of misinformation prediction. Because of the interest of time, I'm going to skip some motivation, because I think it's very clear that we need to do misinformation detection. There's so much information pollution going on. This one shows an example. This woman soldier was falsely accused as patient 0 for coronavirus simply because she attended a sports event in Wuhan in October, but she was never tested as positive. So she actually got a lot of harassment because of this, and many people actually believe this kind of misinformation. The reason is because human is really good at connecting dots, and a lot of the fake news, they usually subtly manipulated the knowledge elements, or maybe they only have like 90% of the true real information and then 10% fake information. So because of time limit, I'm going to skip this introduction, but just showing you the difference between real news on the left side, and the right side is fake news. You can see the highlighted part, they are basically fake knowledge elements. This relation is not correct, and this entity is not correct. And similarly, in many fake captions, they subtly manipulated their events. For example, this person was not leaving, they are instead, or they're not arriving, they're actually leaving. Sorry, they are not leaving, they actually just arrived this facility, but without background knowledge, it's really hard to determine which one is fake. And this one, if you have not been to Italy or Berlin, if you're not familiar with the street scene, then it's hard to figure out which one is fake caption. So yeah, so our idea is to be able to look into the knowledge element level misinformation instead of just do binary classification for every document. We're going to figure out which piece in this document is fake, and hopefully we can fix it and then tell authentic story. So we are going to use the knowledge graph construction techniques that I already described to construct a multimedia knowledge graph from input multimedia news document. And then we take every triplet in the graph as candidate, and then classify that triplet as fake information or true information. So for example, here in this example, there are two pieces of fake information. Number one is the police was not shooting at the protesters in the image, but the caption says they were shooting at the protesters. And the other fake information is this woman was permanently blinded. This information was never validated in any other places in the body text or in the image. So we are going to take every triplet, 2 nodes and 1 edge as candidate, and then use a graph concat to classify this triplet as fake or true information. So the construction of a multi-millionaire graph is similar to what I already have described. The only difference is we also need to build the bridge between image element and the notch element you get from text. So for example, we need to figure out these two shooting events are coreferential. This bounding box is grounded into the place entity. And then we are going to propagate the representation within data modality and also cross media. And then the other bottleneck is that we don't have any training data, because usually the fake news documents written by human will be removed immediately within a short time frame. So we are only able to find around 24 of human written fake news. So it's not enough for training. But because of the nice graph generation models, maybe you can simply generate fake news for training in an automatic way. So the idea is to mimic how human will generate fake news. We're going to look at the automatically construct notch graph and then manipulate that notch graph by several operations, and then use graph to text generation to produce a fake news article. Let's look at the operations we did. So the first one is to simply switch the entities. We are going to replace the entity with the most similar one. And we are also going to add some new relational events. And then finally, we are going to replace some subgraphs. So one thing to note here is that if you simply replace the most popular one with any similar entities, it's very easy for a system or human to detect. For example, if we replace a bicycle with a truck, clearly that's a fake information because truck is not showing in the image. So we are going to avoid doing manipulation for those kind of cross-media entities. We only replace the entity or subgraph if they are not grounded in the image. For example, we are replacing Zambia with Fiji because they are semantically similar, and then generate a new article using the Fiji entity. Okay, so Linfei talked about AMR parsing, and I also talked about using AMR parsing for IE. So we can also use AMR graph, which is much richer than regular IE graph, and manipulate this AMR graph by switching the rows and introduce negations, and then use graph to text generation to generate the fake caption. So here, just showing some examples. Okay, so this kind of notch graph manipulation-based generation method can give both users and the system very confusing articles. So we did a tooling test by showing every pair of real and fake news documents to the real human users, and they were only able to identify 42% of the fake documents, which is good because that means we really mimic how human would generate fake news, and our detector can be much more reliable. So we apply the system to 2 data sets. One is this New York Times data set generated from Grover, which only use language model based fake news generation. And the other is our new data set we released by doing notch graph manipulation. So you can see for both data sets, we achieve better performance, and our data set is a little more challenging than the New York Times news data set. Okay, so here's another successful example. You can see that in the original single data modality or language model based detector, we failed to identify this facility as fake information, but using the cross-media notch graph, we're able to figure out this is fake information. Twin Towers is not grounded in the image. Okay, so most of our systems are publicly available as open source code, Docker containers, and we also have some demos. And if you check our slides, you can feel free to play with them. Yeah, so now I would like to hand over to you. Thank you.
Thank
you. If you have any questions, feel free to put them in the chat, and we can answer them in the break. Yeah, thanks.
So let me share my screen and then put on presentation mode. Okay, can you see my screen?
Yes.
Okay, great, thank you. So another common NLP task where graph neural networks are found useful is machine reading comprehension. So what is a machine reading comprehension? It is a task of giving a question in natural language based on unstructured or semi-structured resource, extract an answer or select a correct answer from a given list. A particularly challenging machine reading comprehension task is what we call multi-hop reading comprehension. In this particular task, the answers can only be obtained based on reasoning across multiple documents. WikiHop is a particularly popular dataset for multi-hop reading comprehension. For this dataset, the input is a question in the form of source entity, relation, unknown answer entity, along with a short list of candidate entities. Then, based on Wikipedia and Wikidata, the multi-hop reading comprehension system selects the correct candidate entity from the given list. The first paper, or one of the first papers that leverage graph neural network for multi-hop reading comprehension is the one from NACO 2019. In this work, they construct entity graph based on mentions from all supporting documents, and those entities are connected with different edge types and relations. So if you see on the entity graph, nodes of the same color indicate that they refer to the same entity based on exact match coreference. And then you can also see this dust ellipses. Those are supporting documents organized as a graph where nodes are mentions of either candidate entity or query entities. And there are 4 types of edges. Document-based, where it means that the nodes co-occur in the same document. Match means that they are exact match of each other. So this is most reliable, but relatively fewer such edges. And then there are also edges constructed based on coreference. These edges will be less reliable. And finally, for nodes are not connected otherwise, also an edge called a complement from in the graph. They're not shown from the example, but in the actual model, those edges are there. So since the graph is not a homogeneous graph and there are multiple node type, the graph representation of each node is learned by entity relation graph convolutional network, while entity relation, a gated version of relational GCNs. So you can see the updated vector of a node is a function of its neighbor conditioned on the relations between them in the graph. The candidate scoring uses final node embedding and the question representation to predict a distribution over candidates. So if we look at the final experimental results, we can make a few interesting observations. First of all, when we replace Elmo by GLAV, right, basically remove a more powerful pre-trained language model with a simpler one, you can see there's still a pretty competitive system, indicating the relational graph convolutional network is useful. Second, based on ablation tests, we can see that if we remove all the relation types, there is a significant drop. So that means that differentiate the different kind of relations are important. And then if we look at removing different type of nodes, and you can see these document-based relations are the most significant. This is because majority of the connections are indeed between mentions within the same document, and also without connecting mentions within the same document, we remove very important information, since the model will not be sure whether they appear closely in the document or not. And finally, the authors also try to replace the heuristic that create all these different edges with one that actually predict those edges. As you can see from the last results, this result to a significant drop. In fact, it's worse than the baseline that there is no graph neural network at all. This suggests, this model of induced edges is not working, and really learn how to predict edges is still a very hard and open problem. A lot of people working on this kind of thing, right? Like think about the predicting edges in the graph, in a knowledge graph. And then another interesting observation we can make is that as the number of candidate answer or nodes increases, both lead to larger and more complex graph, and therefore you can see worse runtime performance. So in the work I just described, the entity level information is taken into consideration when constructing node. The follow-up work later in the year by Tu et al. Seeks to take information from different granularity into consideration. So they consider nodes constructed by candidate, document, and entities. It first generates query-aware candidate, document, and mention vector representation with co-attention and self-attention, where co-attention enables the model to consider codependency between query and document, query and candidate and mention. And the self-attentive pooling summarizes the information presented in the co-attention output by calculating a score for each word in the sequence. In addition, it also, and you can see from this example graph, right? The three kind of nodes rather than just one type. So we have document nodes, candidate nodes, and entity nodes, and also introduce additional type of edges compared to the work we just described earlier. So we have document candidate and document and entity, whether the entity extract from the document, candidate and entity, whether the entities are mention of the candidate, entity and entity, if they are extracted from the same document, or if they are exact mention of the same candidates from different document or other pair of entities. So you can see it's also a heterogeneous data graph, but it just includes additional type of nodes and edges. So overall, the contextual embedding are initialized in the graph. I gated the GCN used to train the node representation in the graph. And we can see the overall structure is similar, right? I gated the GCN used to train the node representation in the graph. So the final node representation of candidates and entity nodes corresponding to mentions of candidates are used to calculate classification scores. And then we can also look at the study based on ablation test. We can see the graph is very effective. When we remove the graph, we can see a very significant drop. And also the edge types are very important, and entity node scores are most important. Are more important than entity nodes are the most important. And if you recall, right, the earlier work focused on entity nodes. So you can see even though there's some improvement, because most of the information already been captured by the simpler graph, that one also achieved pretty good performance. And similarly, we can see as the number of supporting documents or number of candidates increase, the runtime performance also decrease, and also accuracy decrease as well. So this is reasonable because most document means more entities and bigger graph, and therefore more challenging for reasoning. So another interesting reading comprehension paper is this one on textbook question answering. So in this particular setting, the resource include both visual content as well as the textual content, because this is related to like reading a book and then making multiple books and then try to answer questions over those books. So this is required to solve a multimodal question answering problem. And the questions themselves could also be text related or diagram related questions. So the key challenge is, first of all, it contains both visual and textual content. So this is a multi-modality problem. Also, when we come to textbooks are obviously much longer than typical kind of document. So how do we take the long context into account is also important. Another thing is also every textbook kind of related to different domain, right? So it's very difficult to solve unseen problem. Like for example, if you read 2 books, you can probably answer questions over those 2 books, but how do you answer questions over other books you haven't read yet? So this is another challenge in the problem. So we will describe shortly how do we, how did the authors resolve all these challenges? So on the high level, we can view the system has 2 main steps. The first is preparation step, where the context M is determined by TF-IDF score with the question and the case answer. Then the context M is converted into a context graph M. The question and case answer are also embedded by graph and character embedding. So this step is also repeated for all the candidates. The second step is the embedding step, where RNC as a sequence embedding module and FGCN as a graph embedding module. So with the attention method, the authors obtain combined feature, and then after concatenation, RNs and the fully connected module predict final distribution in the resolving step. Because the constructed graph is an undirected graph, and the authors then apply graph convolutional network to encode the graph. So textbook questions are very domain specific, as we just described, right? So it's very difficult to use training data to help predict unseen questions. So in this particular work, besides applying graph neural network, it also introduced an interesting step called self-training to help the model learn to read, to understand the textbook and problems in advance with the help of the teacher. So think of it almost like in order to prepare for exam, you read the textbook without actually taking a course about it. So you may not do as well as a student who has actually taken the course, but it probably is better than you have never seen the textbook before. So the same thing here, you basically expose all this data in testing in an unsupervised fashion to the model, but then that will help later on. We can see with the overall question answering task. So we can see from the ableism test here. So first of all, if we do self-training on training data only, right, it's pretty useful. Even just if you just do self-training, even just on training is useful. And then we can also see the context graph is pretty effective as well. Another reading comprehension problem is conversational machine comprehension. Unlike traditional machine comprehension, the conversational machine comprehension task is to answer a question in a conversational style, giving a passage and a previous question answer pair, then you answer the current question in a thread. So despite the success of existing work of machine comprehension, conversational machine comprehension have proven to be much more challenging. So there are 2 major challenges. First of all, the topic focus usually shift as conversation progress, making it difficult to model a conversation. Also, many questions refer back to previous conversation, right, with the co-reference or ellipsis. So therefore, without fully utilizing conversational history, one cannot really correctly understand a question and find an answer. So we need to address all these two challenges. So in this particular work, in IJCAI 2020, this is the overall architecture. So as we can see from the overall architecture, the framework consists of embedding layer, reasoning layer, and a prediction layer. So for embedding layer, the authors use bidirectional LSTM to encode a question, and another by LSTM to encode context for each conversation turn. The major technical contribution in the reasoning layer. So it has context graph learning component that dynamically construct a question and conversation history aware context graph at each turn to model semantic relationship among context words. And then it also have a context graph reasoning component using a novel relational GM module to model a sequence of a context graph in a conversation, which we will explain a little bit more in the next slides. And finally, the prediction layer predicts answer location by matching questions and context embeddings. So the intrinsic context graph structure is unknown. Moreover, the context graph structure may vary across different terms by considering the change of questions and the conversational history. So in this work, it dynamically builds a question and a conversation history aware context graph to model semantic relation among context words at each turn. When performing reasoning over context, context is viewed as a graph of words that captures rich semantic relationship among words and then apply a recurrent graph neural network to process a sequence of context graph. So this RGNN module combines the advantage of RNN, which are good at sequential learning, and GNN, which are good at relational reasoning. The constructed graph is an undirected graph. The authors apply graph-gated neural network to encode the graph. We can easily visualize the change of the hiding representation of context word between consecutive terms by computing the cosine similarity of hidden representation of the same context words at each turn, and then highlighted words that have small cosine similarity scores. So you can see from this graph, what are the most changing context words between each of the turn in a conversation from the core QA development dataset. So in summary, in machine reading comprehension, when we apply graph neural network, it enables multi-hop reasoning, and also it allows it very straightforward to encode heterogeneous information so that we can capture different kind of nodes and different edges. And here we can construct both statical graph or a dynamic graph in the case of conversational reading comprehension. So the next topic where I'm going to talk about is natural language generation. So natural language generation is a very large topic. So I will focus on a couple of smaller tasks. So the first one is natural question generation. So what is the natural question generation? What it is giving a passage and an answer. Ideally, the generated answers are relevant to the given passage and answer. So this question generation task has many useful applications, such as provide synthetic training data for QA systems. Okay. So this IJCAI 2020 paper proposed a IL-based graph to sequence model for the question generation task. As we can see from the diagram, the model consists of GNN-based graph to sequence generator and a hybrid evaluator combining both cross-entropy-based and IO-based objective functions. In order to better capture the rich structured information hiding in the passage text, they construct a passage graph, which contains each word in the passage as a node, and apply a GNN to encode the graph. And for graph construction, the authors explore two different strategies. First is the syntax-based static passage graph construction, where a dependency graph was constructed. And then is also construct a semantic aware dynamic graph, where the node embedding based similarity metric learning and KN style specification were applied. Because the construct graph is a direct graph and the experimental results. Sorry?
Oh, we can hear you now. Okay.
Okay. Okay, so if we look at the experimental results, we can see the static graph construction performs slightly better. Performs even better. And the graph to sequence performance better than sequence to sequence models. And then the last one I'm going to talk about in terms of natural language generation is code summarization. So based on the name, you can see the input is a piece of code, and then the output is a natural language sentence that describes the code. So this can be very useful in terms of, for example, automatically comments creation. So this IJCAI2021 paper also applies the GNN-based graph to sequence framework for the code summarization task. For graph construction, they propose to first combine the static CPG graph and the attention-based dynamic graph. As for dynamic graph, they apply structure-aware similarity learning, which utilizes the information of the static graph. They also combine the intrinsic static graph and learn the implicit graph for better performance. Okay. For graph representation learning, because the constructed graph is a multi-relational graph, they apply a multi-relational GNN to encode the graph. Specifically, they propose a hybrid GNN, which run messages passing on both static and dynamic graph. So let's look at the experimental results here. First of all, combining static and dynamic graph performs better. Yeah, I think next topic now. Go ahead.
Thanks, Yunya. So I'll share my screen. So can you see me and hear me?
Yes, we can hear you.
Okay, thank you. Hello, everyone. So I will continue with the graph representation and models for text clustering and matching. So basically, my content is related to the application for like graph with information organization, retrieval, and recommendation. So let's start from information organization. So basically, nowadays we're experiencing like information explosion, as we have like many information being produced every day, and it's not an easy task to retrieve what we want to know from the large amount of information. So if you input some queries in a search engine, or you receive several recommendations from like this news stream, you will get a mask document list. So basically, each item is a fine-grained articles talking about some event reported by a specific multimedia. And they may contain redundant information because they may report the same things from just different perspectives, and they're unstructured. because they are a list without any relationship between them. So we proposed the story forest system to try to reduce the redundancy between different news articles and reveal the structure between them. So here we show an example about the story about the 2016 United President selection. So we can see that each green node indicates an event. So here we define an event node as a cluster of documents while they are talking about the same incident in the real world. And we organize different events by the order of time as well as the coherence between them. So if you look at this example, you will see we start from the Trump become president candidate and until he becomes elected as president. And we have several branches here. I said node 3 until 6 is about Hillary's health condition. And node 14 until 18 is about FBI investigating the mail door of Hillary and so on. So in this way, we can actually try to reduce the redundancy of different news articles because the same events are reported by the articles in the same node. And also we can easily track the evolving of related events, which we call the cluster of events as a big story. So here shows the process of the story forest system. So the whole framework of it. So basically, we start from pre-processing the online stream of news documents. So we have a stream of documents which comes in by time, and we will first pre-processing these documents and extract keywords from them. And then the key research problem here is how we can get fine-grained clusters of these news articles. Well, each cluster only contains the articles talking about the same event. So the event is a very fine-grained semantic level clustering. So the idea is we want to compare each pair, the relationship between each pair of documents. But in this way, if you have n documents, then the complexity is O(n) squared, which is very cost a lot of time and resource. So in this way, we propose the event X algorithm, which is a two-level graph-based clustering algorithm. So the basic idea is we first organize, we first perform the first layer clustering by construct a keyword co-occurrence graph based on the keywords from the documents. And then we perform community detection over this keyword graph and assign each document to the most similar subgraph here. In this way, we get the first layer clustering, where each cluster size is much smaller than the whole document set. And then for the second layer, for each document cluster, we will use a classifier to decide whether each two documents are talking about the same event or not. Then in this way, each cluster will form a document graph, where now this node is a document instead of a keyword. And then we perform community detection again for each document graph. In this way, we divide it into fine-grained document subgraphs, where each document subgraph represents the event node. And we have an algorithm to organize this event node become a story tree, while each tree only contains events that are highly related to each other and talking about the same stories. So this system is applied to the Tencent QQ browser or topic list, where if you in the QQ browser, you have the topic list. Well, it is updated in an hourly basis. So every hour it will update the most important hot topics. And if you click on one topic, let's say here shows an example about the topic, how can public with PhD diseases, with the topic several years ago. And then you will see different articles reported by different media talking about this event. And in the system, we talked about the text matching task. Actually, so we need to construct a graph, a document graph in the second layer, which is we need to decide whether two news articles are talking about the same event or not. This is a task of text matching. Actually, text matching covers a wide range of tasks. So based on whether the length of the source and target text, we can divide them into 4 categories. So for example, what we are talking about is the long text matching. And then we have the ad hoc retrieval, which is input short query and output long document list. We also have like short text matching. For example, the question answering, you matching the questions and report searching and so on. And for document classification, sentiment analysis, you input the long documents and output short labels. So here, our core task is identify the relationship between two news articles, which is just like to classify whether they are talking about the same event or two related events. So compared with the short text matching, long document matching has several challenges. So first, they are hard to encode because the length is long. So it's not very feasible to encode the semantic very accurately. And also, the order of the content is flexible. Let's say if you switch two paragraphs in the document, the meaning is not like changing a lot. However, the encoding vector may be changed dramatically. And also the time complexity is high due to the length. So in this way, we propose the divide and conquer strategy. So basically we divide the content of two news articles by subtopics in it. And then we align the corresponding same subtopics in two documents. And finally, we will perform parallel distributed matching, where we match each local subtopic pairs and then aggregate the local matching score to get the final matching result. So to perform such kind of distributed and parallel matching, we first propose the concept interaction graph to decompose the content of a long document into several parts. So here shows a toy example. So this toy document has like 6 sentences. And first, we will extract the keywords in the document. So this is denoted by these red words. And then we will perform community detection for these keywords. Basically, we cluster these keywords into subclusters using a similar method we just presented, which is like we construct a keyword graph and perform community detection. And you can also use any other methods to just divide them into different clusters. And here we call each cluster of keywords as a concept. And then we will assign each sentence to the most similar keyword cluster by calculating the similarity. And finally, we construct a weighted urge. Basically, we concatenate the sentences over each keyword cluster node and calculate the TF similarity. If the similarity is above threshold, we will keep this weighted urge. So this is the constructed concept interaction graph. And if you have 2 documents when you're performing document matching, then for each keyword node, you will have like 2 lists of sentence indexes. Well, they are from the 2 corresponding documents. So based on such kind of graph representation of a document or document pair, we can perform long document matching. So first, we will construct the concept interaction graph as we described. And then we will perform local matching. So basically, now we have a graph of document pairs, where each node contains a subset of sentences from document A and document B. Then for each node, we will perform short text matching using any short text matching methods. For example, we can use we can calculate some features by calculating some different similarities to form this matching result. Or we can use the Siamese neural network. So basically, Siamese neural network, we have like the same encoder for input A and B, and we calculate the encoding vector and put them into the matching layer to output a matching vector. And after that, we will have a graph where each node contains a local matching vector for like some sentences from the 2 documents. And we will aggregate this local matching vector to a global matching vector by graph convolutional network. In this way, we can take the content relationship between these 2 documents into account. And finally, we will classify whether these 2 documents are talking about the same event or not by a classification layer. And all this encoding and the classification layer, as well as convolutional network layers, are trained end-to-end. So this is the experimental result. We will observe that. So first, if you compare these two baselines, so the experiments on the left are baselines, and all the results on the right are our models and our model variance. So if you compare these two methods, you will see that by just divide the content by the concept interaction graph without considering the structure, we actually improved the accuracy and F1 score of the experiments by 4%. And if you compare like these two methods, the only difference is that for the 15th variant, we take the structure into account by aggregating the local ranking vector by the graph functional network instead of just calculating the mean. Actually, we found that using graph functional network combined with our graph representation, we actually improved the result by over 10%. And we performed this experiment on the Chinese news same event and Chinese news same story dataset, which are two datasets we constructed for comparing the relationship between a pair of news articles. Next, we will talk about graph for text mining and classification. So considering this problem, so if you input a query in the search engine, such as a query transformation with a natural speech, we want to infer your interest. So if you receive articles about transformation, you may be not interested. So this is called the inaccurate recommendation, because you may not be interested about transformation this person. And if we recommend articles about transformation with a natural speech, you may also don't want to read it again, because you may already read some articles about this specific event. So this is called a monotonous recommendation, which means we keep recommending the similar articles about similar topics to a user. So a good recommendation may recommend articles about Brexit negotiation to the user. So to achieve such kind of performance, we need two components. First, we need to know that the Brexit negotiation is a potential user interest in a suitable granularity. And the second is we need to infer the relationship between user interests, which means that we need to know that this event, transformation with a natural speech, actually belongs to this topic, Brexit negotiation. And the user, if he or she is interested in this event, maybe he's concerning about this specific topic. So we may think about what are the things people care about. So the first categories are the different events. So we define an event as a real-world incident that involves specific person, organization, or entities with a certain time or location of occurrence. So for example, the transformation with the nation speech is an event. And Apple launched new iPhones are also an event. And another type of user interest we call concepts. So we define concept as a collection of things that share some common attributes. For example, fuel-efficient cars, economic cars, and we think Honda Civic or Hyundai Electron are belonging to fuel-efficient cars. And also the entity Iron Man and Captain America belong to the concept Marvel heroes or Avengers. So we constructed a web-scale ontology to represent user interest and document topics. So here shows the architecture of the ontology. So basically, we have different types of nodes and organized in a hierarchical manner. So here, the category nodes are like high-level categories. For example, current events, technology, and so on. So these nodes are defined by humans, which contains like about 1,000 different categories organized in 3 levels. And we have many nodes mined from weblogs. So for example, these are the concept nodes, and these are the topic nodes and events nodes. And we have different entities. And the major relationship in this ontology are the either relationship, which indicates a topic is belonging to a category, or even it's belonging to a topic and so on. And we have the involved relationship in case some entity or some concept is involved in a topic or event. And we have the correlation relationship. If like two entities are always mentioned together or mostly mentioned together, we think they have a strong correlation, and this relationship will be identified between the pair of entities. So this is a framework how we actually mine such kind of ontology from such logs. So starting from user activity on the secondary, so then we will have the search click graph. So basically, it means the different user queries, and these are the top click documents for each query. In this way, they form a bi-party graph. And then we will perform some bi-party graph clustering to divide it into several query document clusters, where each cluster contains a few highly similar queries and the corresponding top click document. And then for each query and document cluster, we want to extract a potential user interest phrase from it. For example, this phrase can be a concept or can be a topic or an event. And after we extract these phrases, we can organize them in a hierarchical manner by some heuristic approaches or statistical approaches. In this way, we will have this user attention ontology, and it can be applied to tag the user's interest or perform story composition or perform document tagging. Basically, we tag the phrases to a document to indicate the major content of it. Or we can perform query conceptualization. So if a query is talking about some entity, we may infer the higher level concepts which this user may be interested in. So in our giant system, so basically we call this system as the giant system. So in this system, the core research problem is like how we can extract heterogeneous phrase as user's interest from the query doc cluster. So here shows an example. So let's say we have this query, and we have this document where we show the titles of the document, and we want to extract a concept which is a Hayao Miyazaki animated film. If we look into this example, we will see some characteristics of the output words in this concept. So first, they will show some patterns in the query and titles. And second is that they will show up multiple times. You will see that most of the words in the concept are shown in all of the query and titles. And third is NER and part of three tags are useful features to classify whether a word in a query or title can be a word in the output concept. For example, most of them will be named entities instead of like some stopping words. And most of the time, there will be a continuous chunk. So sometimes you will have some stop words within this phrase, but most of the time they are just continuous. And finally, the syntactic dependency will be similar in different query and titles, even though the context words are different. So to fully utilize these very informative features, we construct the query title interacting graph. So basically, for given a set of queries and titles, for each node, it represents a unique word in the query or title. And then if two words are adjacent in any of the query or title, we will construct the sequential edge between them. And if they are not adjacent together at any place, but they have a syntactic dependency between them, we will add the syntactic dependency. And finally, for each relation, we will add its inverse relation. And also for each query and title, we have the virtual start of sentence and end of sentence node. In this way, we form this graph representation of a cluster of queries and titles for our heterogeneous phrase mining. And this shows like how we actually perform phrase mining. So first is we will classify whether each word is like the output word belonging to the phrase. For example, belongs to the concept or the event. Basically, this is a node classification problem, and we model it by the relational graph convolutional network. And the second part is like how we can actually concatenate all these different word nodes as output phrase. So our idea is that as they are like usually a continuous chunk, and we want that we can find the shortest path start from the SOS node until the end of sentence node. And this shortest path will concatenate all the positive nodes to form the phrase. This is actually the asymmetric traveling salesman problem, and it can be solved by many algorithms. So for text matching, so basically the idea is like we can modeling the text or a corpus as a graph and perform node classification or graph classification. So here for this text DCN, it models words and documents as nodes, and the edges are co-occurrence relationship between word pairs and the TF-IDF between word and document. And then it models the graph with a graph convolutional network. So these are the results from the paper. If you check it, you will see that actually when you incorporate the graph convolutional network to modeling the graph structure, it can achieve a much higher performance when the training data is limited. And if you check the right part, you will see that the text DCN can learn very discriminative representation of the documents. And also the second layer representation is more discriminative than the first layer, which indicates the encoding vector learned by text DCN is very helpful. And the multi-layer DCN is useful than single layer. And this is another work which proposed as text ING. So the difference here is that they perform inductive text classification by modeling each document as a single graph. So it will consider more fine-grained intrinsic structure of the document. So here the nodes are the words in a document, and the edges are the co-occurrence. And it models the graph with a gated graph neural network. And it can generalize to new words that are absent in training, therefore applicable for inductive circumstance. And here we can see that the text ING performs better than the text DCN. So basically, by combining all these different techniques, we apply our giant system to the this news recommendation in different applications. So here shows the application. So basically, if you have like different news articles in the news stream, it actually we have the implicit tagging for each document. So for example, for this document, the title is "See this class with less than 12 per 100 km fuel consumption and up to 100 km recharge milling." So we tag a concept low fuel consumption cars to this news article. But actually, you can see that the text in this concept is never shown in the title of the document, which means that we're not performing some text matching. We're actually tagging the appropriate text to the article based on its semantic content. So to summarize, the graph neural networks enables the encoding of multi-scale information and heterogeneous information for different applications. Thank you.
Thank you, Bang. Let me share my screen again. Okay, so far we have been talking about a lot of different NLP applications. Now let's talk about how can we leverage some our developed library called Graph NLP library for making it easy using with the graph units for various NLP applications. So our Graph NLP library is the first library that developing for deep learning on Graph NLP. So this is overall architecture of our library. You can see here that so we support the CPU, GPU in terms of hardware, In terms of backend framework, currently we support PyTorch. The TensorFlow variant is on the way. Runtime library, we are using DGL and Hugging Face. The reason we're choosing DGL because it's high running efficiency for the large graph. And the core part is our Gradual NLP library. We have 4 different layers. In the first layer, we have our graph data and the data set. And then in the second module layer, we have a graph 5 different modules, graph construction, graph neural nets, prediction, and loss and evaluation. So in order to promote this graph-based encoder-decoder model, we also have a model layer that is a graph sequence model and graph tree model, so that you don't have to implement this from scratch. I can directly use that for your application. And then we also support more than 12 different applications, have example code there, so you can either directly use them or you can customize based on your own applications. So these are key features about our library. So it's easy to use and flexible. We have a rich set of the learning resources for you to use. And because we built on the DGL library, it's a highly running efficiency and its ability. We also have a comprehensive code examples for you to start so that you can have a quick start of using how to use our library, or you can even explore more for more advanced using usage of our library. Currently, we are very soon to move from the V0401 variant to Alex variant. In this new variant, we have several new features. We have a easy inference. We have a complete documentation. We have a full code lining. And also in the future, we are going to also to further improve the graph topology and embedding optimization so that they can easily use of that without any redundancy, and also provide more user-friendly API for inference. So this is a deep dive into our graph NLP library. As you can see here, that so our tutorials almost follow the same structure of our library. So this is a data flow for you to easily understand how the Graph NLP library works. Basically, you have a raw text document, and then you send it to our Graph NLP library. We will do the graph construction for you, and then we have this graph data inside library, and then we will pass that to our GM module so that we can generate variants of the graph node representation, and then you can send to any downstream task for to do the prediction, and then you can evaluation and then do the loss computation. This is compute flow for our Gradual NLP library. You have 2 scenarios that can sit here. Either you already have some graph available. In that sense, that you can directly pass to the graph data module to do the topology construction and embedding construction, and then go to the dynamic construction. This is optional. And then we can have the graph level representation module to generate the graph level representation, and they can do the different tasks, like document classification, link prediction, graph prediction, or you can do variants like a sequence tree decoder. So more commonly, you may have a text sequence. So in that case, so you can either do like static graph construction and then pass to the graph data, and then have a dynamic graph construction, or you can do skip this static graph construction part and later to do a dynamic construction, or you can do both. So this is really your choice. Yeah, this is very easy to use. So this is kind of like a replicate of the all variants of the experiment published in the all the step art paper. I can see that so we use a different module and a different construction and different evaluation metric, and to try to see that so if to show you that so our library really is very good to reproduce all this result. And so by introducing our high-level architecture of our library, now I'll pass to the Yu to talk about the 2 code examples, so that you can have a more global picture and low-level details about our library. Yu, it's your floor now.
Thanks, Linfei. Now let's see some demos. We can use the Graph NLP library to use real-world applications. So first demo, let me share my screen. Demo I will be introduce is the knowledge graph completion demo. So but before talking about the demo, let's go to our Graph NLP demo repository. So this is a GitHub where we host a few demos based on the Graph NLP library. So in order to run our demos, we will need to first install the Graph4NLP library. So we can follow the environment setup instructions here to install the library. And one thing to so our library relies on the Stanford CoreNLP library to do static graph construction. So remember that for static, we will need to use a few like NLP parsers to build, for example, the dependency graph, constitutive graph, AMR graphs. So in our library, we rely on the Stanford CoreNLP library to do this. And so, but like for this demo purpose, you will not need to install that because we already provided the pre-processed data in the demo. So you can directly run the demo after installing the Graph4NLP library. So once you install the Graph4NLP library, you can start with the Jupyter Notebook server, and then you can run a few demos provided in this repository. So the first demo I will be introducing is the knowledge graph completion. So in this demo, we use the Graph4NLP library to build a GN-based knowledge graph completion model. So the model consists of a graph embedding module where we can use like different GNs to learn the node embeddings. For example, in this demo, actually in this demo, we provide a few options, including like GGN, GCN, GAT in the graph stage. And this model also consists of a prediction module. And in this demo, we also provide a few options. For example, we can use this distant model decoder, which was proposed by some previous models. So yeah, so here's a demo. So you can directly run this demo after installing the Graph4NLP library. Let's go back to the slide to talk about some various components in this demo. So here we can see the overall architecture of the model. So as I just mentioned, like the model consists of a GN-based encoder. So here we directly call the high-level GN API. So here we call the GGN API, but you can also choose to use other GN models, like for example GCN, GAT to do that. And also in our GN implementations, we also provide an argument, which is direction option, which user can specify whether we want to use a bidirectional GN or the unidirectional version of the GN. And that's for the encoder part. And for decoder part, we can just call the mount decoder API provided implemented in this demo. So once we define the model architecture, we can just call the APIs to learn the graph embeddings and also to do the prediction. Yeah. Now the graph data APIs. So the Graph4NLP library provides graph data APIs which can support arbitrary node edge features. And also the graph data APIs provides very flexible operations, as you can see from this code piece. So what it does here is that we construct a graph using the graph data API by adding every pair of nodes to the graph data. And then we can also store the edge attributes, which is as we can see here. Yeah, so that's for the knowledge graph completion. Now let's talk about another application, which is a math word problem application. So you can still go to the demo page. So this is the demo page of the math word problem. So in this demo, we are focusing on the meta problem solving task. So this task aims to infer math equations from natural language problem descriptions, where the math equations can be naturally represented as a tree. That's why we can regard this problem as a graph to tree problem, and then we can apply the graph-to-tree model to solve the problem. And the Graph4NLP library provides the high-level graph-to-tree APIs so that we can directly call the graph-to-tree API to build the model. And let's go back to the slides. So, so this is how we can call the graph-to-tree API to create a model instance. So, for the graph-to-tree API, like the library provides like various options in terms of the decoder part. Like for example, it provides attention mechanism, copy mechanism, and a coverage mechanism, which are very widely used in those like sequence-to-sequence models. But we can also apply those techniques for the graph-to-tree models. And here is our dataset API, so which provides a bunch of options. For example, users can define like which type of static graph construction approaches we want to use. For example, like either it's dependency or constituency or IE graph and so on. And also users can also choose to apply like a dynamic graph constructions for by calling our API. And also we also provided the option to combine the static and the dynamic graph construction approaches. Yeah, so that's for the demo part. Okay, I'll pass it to Lin.
Okay, thank you. Okay, finally, we have reached the fifth direction and the conclusion. So as you can see here, that the rising of the graph neuronals and NLP really it's attract significant amount of interest in the recent years. This is some statistical calculation about what's the recent the number of submissions in the very top ranked conference. So moving forward, we are see that there are several future work that still have a lot of potential that we can explore. For example, for the graph construction part, so how the dynamic, we can see that they have a lot of the exploration in the static graph construction, but in terms of dynamic graph construction, they are largely unexplored. How to effectively combine the static graph and dynamic graph so that we can achieve the to generate the optimized graph for the downstream tasks. And even for the dynamic graph itself, currently people only explored like homogeneous graph, but how to construct the heterogeneous graph, just like we have been using static graph construction that we can have easily have a heterogeneous graph, right? So, and also how to make a dynamic graph construction itself scalable is also very important. So similar to the graph construction part, so we have been observed that more and more people right now using graph neural for the logic graph, but most of the logic graph today is easily can have more than 1 million graph node. So how to scaling graph neurons for a very large graph also is very important, especially for multi-relational and heterogeneous graph neurons. We have also see the two big trends like graph neurons and transformer in NLP. And right now, this is almost like two most popular architecture, especially for transformer. So how can we effectively combine advantages in both graph neurons and transformer? It's a very interesting topic. Although we have been talking about the graph transformer a lot, but is this graph transformer the best way to utilize the advantage of both worlds? And also have seen starting from 2019, the pre-training model have been starting kind of like dominate the NLP world today as a kind of like a unified learning paradigm for many NLP tasks, especially when we see BERT and GPT-3 have been produced state-of-the-art performance in many NLP tasks. However, although pre-training is a very, very important learning paradigm to learning for the big model and then fine-tune in this specific domain, it's essentially still limited to the input that have a text sequence. It's a sequence input. But in reality, maybe you have other information, right? For example, we have this social network, have this knowledge graph. This is also very important wisdom and knowledge, but it already present in graph format. So in that sense, so graph analysis seems like a small general learning paradigm to absorb different input source. Therefore, so how to do the pre-training for graph analysis for NLP domain is also very important, especially, for example, in the information retrieval and search domain. So we have also talked about a lot from Professor Chi's talk, how to do this graph model for solving, leverage the MR parser for the IE problem. So in general, this is not limited to the IE. It also can be doing for other things. For example, even for the AMR parser itself, the problem is trying to transform the original text into the AMR graph. So if you treat the input side as a graph, then essentially it's still a graph transformation. So is there any like generic model for graph transformation so that can solve any kind of like graph transformation problem in NLP? This is also a very interesting direction. And how to do the joint text catchy reasoning in NLP by giving the fact that we have already explored for GN for the many for the multi-hop reasoning problem, but not really joined with text and catchy. And also we can also consider to incorporate the source and context into the knowledge graph construction and verification. This is more like in the IE domain. Okay, so now let's conclude this tutorial. So as you can see, that deep learning on graph or NLP is really a fast growing area today. So we see the advantage of graph analysis is because that it's really provide a way to bridge the gap between combining the empirical domain knowledge and the power of the deep learning. So when we have an NLP task, so there are basically two important things we have to consider. First, how to convert text sequence into the best graph. Is a direct graph, multi-direct graph, or history graph with what kind of a graph construction technique we're using. And later, once you have a construct graph, so what kind of graph representation learning technique we should leverage so that we can make full use of the graphs that we have been constructed. And here we provide first a library called Graph for NLP library for you to make full use of the graph analysis for NLP. Here we have a website, survey library, and you can feel free to visit them and to see that if it's useful for your applications. Finally, we also can summarize. We have been doing this tutorial in many different conferences, early from the LACO this year in summer, in June, and then to IJCAI, and then to KDD, and this is our first one in IJCAI. We are very glad that we have been receiving many different feedback from our audience. And here is we summarize a list of the questions that people have been asking very often. So we will first leave time to our audience to ask questions that you have. But if you think that your question is already being covered by this topic, so then we can go through this FAQ and talk about our opinion or comments about this very frequently asked questions. So if you have your own question, you can post in the chat, or unmute yourself to ask question directly. Okay, otherwise, probably we just to go through this list. Okay, then let's go through this FAQ list. So the first most frequent asked question is, so how do we compare graph analysis with transformers? And yeah, this is a very interesting question. Who wants to start first to talk about your opinion about this question?
Yeah, maybe I can start first. Yeah, so I think there are many connections between GNNs and transformers. Transformers actually can be regarded as a very special case of GNNs, where the multi-head self-attention in transformers is essentially learning the dynamic graph structures adaptively at each layer. And also compared to like transformers, like GNNs are able to encode arbitrary graph structured data, which can augment the raw text with rich structural information, as we previously mentioned in the tutorial. I think that's really one of the biggest advantage of GNN models compared to the transformer models. And I believe encoding rich prior knowledge about text is very helpful for some NLP applications. So that's why I think GNNs can be beneficial for many NLP tasks compared to just transformer models. And also, like our previous experiments also showed that the GNN-based graph-to-sequence models actually outperformed the transformer-based sequence models on many natural language generation tasks. And yeah, that's my answer for this question.
Okay, now let's move to the second one. What's the difference between GN versus BERT? Which one is better? That's people asking a lot about this.
Yeah, I think this question is kind of similar to the first one. So basically for a transformer-based model like BERT, we're trying to like discover the latent relationship between words or different text spaces. And they are basically homogeneous, and we can try to define different, try to learn different relationship by some kind of mechanism, for example, the multi-head attention, so that we have different attention mechanism to form different relationships. And we can abstract this kind of relationship through the multi-level transformer. And for GNNs, when your data structure, when your data actually contains the very explicit or heterogeneous urges, which is explicitly defines the nodes and the neighbors to different nodes. In this way, applying GNN will be a more directed way to fully incorporate this kind of relationship, to incorporate the neighboring or multi-hop information from the structure, from structured context of it. And in this way, we can improve the encoding of the nodes or the urges based on the task you are working.
Okay. So let's want to be why GN helpful. This one seems very, very general. We have been talking a lot about this. Okay. So, okay, if no one take a question, I will take a question. So basically, we have been discussed a lot about why we are using graph neurons for our particular problem. That's really because that the graph neurons is one type of the deep learning on graph technique, but it probably is the most popular one in the current community. The reason that it's very easy to use. I have a lot of library that you can make it very easy with that, like DGL or the Python geometric. But most importantly, that I try to take a relational data into code so that you can improve the graph node representation for your downstream task. Okay, maybe let's move to the next one, pre-training GN for NLP.
Yeah, maybe I can talk a little bit about this question, pre-training GNs for NLP. I think this question is also related to the previous question, which tries to compare GNs versus BERT. I think when we compare GNs and the BERT, it's not a very like a fair comparison, because BERT is pre-training transformers for the NLP domain, and that's why I believe like pre-training GNs for NLP is a very interesting problem, since there are many connections between GNNs and the transformers, and also GNNs provide additional benefits of like encoding the prior like structural knowledge about text. So since we have seen a lot of success from like a pre-training transformers for NLP, then I think probably we can expect to have some success from like pre-training GNs for NLP. Like even though it's a very promising direction, however, like pre-training GNs for NLP is underexplored. Like personally, I haven't seen any research papers about pre-training GNs for NLP, but as Lin-Fei mentioned in the when talking about the future directions about the GNs for NLP, I think pre-training GNs for NLP is really promising because it can additionally like encode the rich structural information during the pre-training process, which can be beneficial.
Yeah, and I think like if we compare pre-training our graphs with pre-training our text corpus, so the one essential aspect we need to consider is like whether the pre-trained graphs can be helpful to our downstream tasks. So if so basically, if let's say our target task has limited training data, but we have like another data set which contains similar information compared to our target task. And in this way, we can try to pre-train the graph neural network on the available large data set to learn how to like learn information from similar structures or similar neighborhood information. So basically, we need to like try to identify the relationship between the pre-training graph corpus with our downstream task.
Yeah, okay, thank you. The next one, how to train GN on large scale graphs. Yuyao, would you like to share some of your thoughts? You mute yourself. Oh, we cannot hear you. You have to unmute yourself first.
I'm having some problem with Zoom, so it's not showing up on my screen. So what's the question? Sorry.
Oh,
I think I'll mute myself, but like.
Yes, how to train GN on large scale graphs. Maybe you can talk about some applications that you have with some experience.
Sorry, I missed your question. Can you say that again?
How to train graph neural nets on large scale graphs.
How do we train large neural net graph?
Yeah, on large scale graph. Yeah, on large scale data. Yeah, graphs or data set. Yeah.
So I think it's a very hard question to answer. First of all, like what do you mean by large scale? Like how large is considered large scale? Is it a question from audience or?
It's question previously from the audience, and we'll collect this question here and try to discuss this question. So this is all open question. Yeah. So yeah, just based on some.
I think. Yeah. In general, my experience with graph neural network is that it's I think I would say like scalability is still a big issue, right? So my suspicion is that we actually not just innovate on the algorithm side. It may be very beneficial to think about hardware acceleration. So I can, yeah. So some of my colleagues actually did some work, not specifically for graph neural network, but they did a lot of work on accelerate deep learning models. Yeah, I feel besides the normal thing you have on GPU and so on, the further innovation you can do for facilitate the training of the large scale graph neural network. Yeah, as you said, it's an open question. I don't really have a good answer. I think there's some direction we should explore. And I know people are working on that, but right now I have to say it's still an open question.
Okay. And previously, I see you tried to talk about this topic. I believe in your logic graph, for your IE graph, you must have a lot of things that made such a large scale graph.
Yeah, so I think this question is very vague. Are we trying to address the quality problem or efficiency? Normally, we just try to take advantage of everything we have, right? So in IE applications, normally we have a pre-trained model for nodes, and then we usually use GraphGN to update the representation. And then sometimes when you have domain knowledge, for example, when you're doing chemistry domain IE, you try to fine tune that for the target domain, collecting all the scientific papers for that domain. So can someone elaborate the question for me? I'm kind of as confused as in your.
I think some people, when people ask the question, they're really wondering that. So when they have a really large scale graph or large scale the data set, so can we easily use the graph news for such applications?
Yeah, I don't see any bigger challenges than other flat graphs. Flat models. So. Yeah,
that's true. In general, in general, I think it really depends on. So when we talk about scalability, so we just have this a roundtable discussion about the graph news in VLDB. Scalability is one of the big issues that we have been talking about there. So I think it's when we talk scalability, there are two factors that we have to consider in mind. One is size of the graph, other one is the latency. So if we only talk about the size of the graph, can graph news deal with? The answer is yes, because even for DGL library right now, you can deal with a pretty large graph. It may take a long time to train, but it's okay. Just like transforming take a long time, 1 week or even 1 month to train a model. So, but if you also consider like you want to have latency constraints when you deal with a large graph, that's a completely different story. Yeah, that require a lot of the organization in terms of what kind of graph news you should use and what kind of specific component you should tailor so that you can satisfy your latency requirement.
Yeah, I agree. When I think about the scalability, right? Here the scalability, not the size of the graph, is really about the latency and how much time it took for training. Yeah. And even inference time is also important, depending on the application.
I think for large-scale graphs, so basically we cannot directly train on the full graph. So we need like a good method to sample subgraphs from it and use these subgraphs as batches to train over it. So basically, so the most important trick is like how we can choose the appropriate neighbors for each node and for meaningful subgraphs, and choose the appropriate size to maximize our utilization of the computational resource and try to reduce the training time.
Okay, then now let's move our last question. Which graph construction method is the best and how to choose? I think this question is very general. So it really depends on your perspective. It's a learning perspective or it's from application perspective. So yeah, so let's try to address the question from the two different perspectives. Who want to share first?
So I think you already gave the answer, right? You already said it depends on the applications. So in NLP, I think one special thing is whenever we have a preprocessed graph, right, like using semantic parsing, we have different types of edges. And in our IE experiments, we always found edge conditioned GAT, for example, usually performs really well because it just naturally fits the way that the weights can be dynamically assigned based on the different types. So I think if you have reliable construction of heterogeneous graph, then any attention or any model that can capture the topological structure can always help. And if you care about efficiency, maybe GCN is better.
So actually, so when I was doing my thesis defense, actually I received the same question. So basically, my answer at that time is like, first we need to decide what is what we are interested in. So in the task. So if we are working on a word level task, then we should choose the words as nodes. Or similarly, if we are working on sentence level or document level, then we will decide like what is the node in our graph construction. And the second is like what kind of relationship are helpful to improve the performance of our task, whether it's like the word occurrence or the syntactical feature or the like word and the document occurrence feature and so on. So if you think if you're not sure, then the most easy, most directed way is that you can include any urge you may be like maybe useful for a task. And in some cases, you may not even know like what is the urge you want to construct. Maybe you can try to utilize some method to learn to form more high-level urges from the most basic level relationship. For example, the adjacent relationship or word product relationship and so on. Yeah, so it's basically the key idea is like decide the nodes and the urges you are interested in a task.
So we actually have a question in the chat.
Yeah, okay, let's take a look. Okay, one more question here. So for test classification, a simple NLP task, do you still see advantages of GN over models like LSTM and transformer that directly operate on text sequence as an input? Yeah, I think probably this question is good for Bang. Yeah, talking about the test classification task.
Yeah, I think from the result of the text GCN or text ING, we can say that actually utilizing the structured information in long documents, it actually like can improve the performance when you have like very limited training example. And intuitively speaking, for example, the similar documents may have similar structure in terms of the writing style and so on. So in this way, the structured information can have like give you a high level information about the whole document instead of just considering them as a like a sequence of words.
Yeah, I would say in general, there is no one best model, right? For text classification, it's highly dependent on the data and what kind of model you are looking for. So for example, right now I'm leading a project called the Auto AI for text. And in that project, we automate the whole thing, model composition, neural architecture search, and so on. There we run over a million benchmark data set, and there is no clear winner, whether transformer or LSTM or even SVM and so on. Yeah, I would say you have to look at your data and the particular type of model, right? What's the characteristics of model you are looking for to make the decision? And I also, right now in our auto text project, we haven't really incorporated GNN, but we did some initial experiments over a certain data set. It does perform better in terms of accuracy. So I think it's definitely a worthwhile type of model to consider if you are consider text classification task.
Just want to add a little bit about another potential direction is to use GN to generate training data automatically for classification. So you can synthesize some graph to text generated data for augmentation. So I showed some examples in the missing information detection task. I mean, it's kind of binary classification problem, right? You want to detect this fake, document is fake or real. So because of lacking retraining data, but if you can transform some real documents to fake documents by manipulating the graph and then use graph to text generation. That's how we acquire the training data automatically. I can imagine when you have an imbalanced problem in your training data for document classification, maybe you can also generate documents for a new class in such an automatic way.
Yeah, I can also talk a little bit more about this text classification. So when we talk about text classification, there are two in general, there are two like settings. One is the supervised setting, the other is the semi-supervised setting. Like for the supervised setting, we try to, given a document, we try to predict the label for that document. And when we apply students for this task, typically we will construct a graph for each document. Then we apply students to learn the graph level representation. Then we do a prediction. Like I think the benefit of students here is that we can encode like rich prior knowledge about the text. So instead of regarding the text as a sequence of tokens, then we can like we can augment the text with rich prior knowledge by converting it to a document. And that's one setting. The other setting is the semi-supervised setting. Like we have a corpus of documents, and we only have labels for a few documents, and we want to predict the document labels for a lot of unlabeled documents. I think in this setting, people typically, so we are applying graph neural networks, people will typically construct a graph for the whole corpus, where each node in the graph is a document. And then like by doing that, like we can have a lot of flexibility to add many like relationships among documents. For example, if two documents they share the same topic, then we can add an edge. Like if they mention the same entities, then we can also add some edges. So as a result, we can have a heterogeneous graph to represent the corpus. Then we can very naturally apply GNNs to capture all those kinds of relations among documents. That will usually like lead to improve the performance. Yeah.
You're muted.
Hey, I think that's what concludes our tutorial today. Thank you all. I think we still have 4 participants in the chat. So thank you all for joining our DLG4NLP tutorial, and hopefully you will enjoy the rest of the IJCAI conference and have a great weekend.
Thank you, everyone.
Thank you.
Thank you. Bye-bye.
Thank you.
Bye-bye.